Saint Petersburg. The 6th of August, in the year 1753, a heavy summer evening, the sky closing slowly over the city, and the first smell of a storm drifting in through the open windows. In a house that belongs to the Imperial Academy of Sciences, a professor of physics named Georg Wilhelm Richmann is sitting with a few colleagues when he hears, far off, the first low roll of thunder, and in that moment he does not feel the thing that you or I would feel. He does not feel the instinct to close the windows and step away. Richmann feels the opposite. He feels a small, bright urgency, almost a kind of joy, because this man has spent months chasing exactly this, a storm. He needs a storm to finish an experiment that has taken hold of him and will not let go. So he excuses himself. He calls for his engraver, a man whose job is to sketch what happens so there will be a record, and together they hurry across to his own house, where Richmann has built a strange apparatus of his own design, an iron rod that climbs all the way up to the roof and comes back down into a vessel below, a machine built to catch and to measure the electricity of the sky. Richmann wants to be the first human being to put a number on the fury of a storm. He wants to measure the lightning. He reaches his house, he leans in toward his instrument to read it, and his engraver, a man named Sokolov, lifts his pencil to draw. And then, from the iron rod, without a sound of warning, a ball of pale blue fire about the size of a fist leaps straight at Richmann's forehead. It is not an ordinary bolt. It is one of those rare and strange things that even now, in our own century, science barely understands. A floating sphere of electric light. It strikes him between the eyes and it kills him instantly, without a cry, without a single moment of pain. He falls to the floor with a small red mark on his forehead, no bigger than a coin, and one of his shoes has burst open, as though something inside it had exploded. A dry crack, like the firing of a small cannon, tears the door from its hinges and leaves Sokolov stunned on the ground, his clothes scorched, alive only by luck. Georg Wilhelm Richmann had just become the first human being in recorded history to die while experimenting with electricity. The first person to give his life to a force that humanity had only begun to touch with the very tips of its fingers. He had made a single mistake, one small and fatal mistake, and it was that he himself was connected to the ground through his own body, offering the lightning exactly the road it was looking for. The news of his death traveled across Europe and then across the Atlantic until it reached the hands of the very man whose experiments Richmann had been trying to repeat. A printer and politician from Philadelphia named Benjamin Franklin, who would print the story in his own newspaper with a strange mixture of respect and warning. Tonight, we are going to tell the story of that force, the story of electricity. And it is very likely the most astonishing story there is, because it is the story of how human beings learn to tame the lightning, how we learn to take the very same fury that killed Richmann on that stormy evening and fold it into a wire, into a plug, into a light bulb, into the screen that may be glowing somewhere near you right now. We learn to milk the thunderbolts and to hand them out gently to every house in the world, so tame and so obedient that a small child can turn on a light with one finger and never feel the slightest danger. And yet that same force is still, underneath it all, the thing that burst Richmann's shoe. It is the same thing that runs through the nerves of your body as you listen to this, the same thing that is making your heart beat right now, in this exact moment, with a tiny spark that has repeated itself, without rest since before you were born, and that will not stop until the very end. You are made of electricity. You live inside a civilization made of electricity, and you almost never stop to think about it, the way a fish never thinks about the water. Tonight, we are going to think about it, slowly, without any hurry, letting each piece of the story settle into place the way you settle into bed before you fall asleep. We are going to meet the people who chased this force, and they are among the strangest and most wonderful characters that science has ever produced. An old man who flew kites into thunderstorms, a doctor who came to believe that life itself was electricity after watching the legs of a dead frog begin to dance, another man who brought movement back to the corpse of a hanged murderer, in front of a room of horrified surgeons, and who, without meaning to, helped inspire the novel Frankenstein, a poor bookbinder with almost no schooling, who became the greatest experimental genius of his century and turned down a knighthood out of pure humility, a quiet Scotsman who discovered that light and magnetism and electricity are all, secretly, the same single thing, and who died young without ever seeing his idea confirmed, and a lonely, obsessive genius who ended his days penniless in a hotel room talking to pigeons after dreaming of giving free electricity to all of humanity. And in between all of them, we are going to understand, truly and gently, what electricity actually is, what that invisible thing is that runs through the wires, why, when you flip a switch, the light appears in the very same instant, even though the electrons inside the wire, and this will surprise you, move more slowly than a snail crawling. What does a magnet have to do with a piece of wire? Where does the electricity in your home really come from? And why is the answer, almost always, something as simple and as beautiful as spinning a magnet? Why is a bolt of lightning hotter than the surface of the sun? How can a fish build 800 volts inside its own body? And why are you, right now, a warm and silent electric machine that runs on salt dissolved in water? There is no exam. You do not need to remember any of it. If you fall asleep by the time we reach the frog legs, or long before, that is perfect. That is exactly what this is for. Just get comfortable, let your shoulders drop, let the voice carry you, and let us begin at the very beginning of all of it, which is not in a laboratory, and not in a storm, but in a small yellow stone that the ancient Greeks used to rub with a cloth more than 2,500 years ago, without ever understanding why that stone seemed, all of a sudden, to come alive. The yellow stone was called, and is still called, amber. It is not really a stone at all. It is the resin of ancient trees, sap that dripped from their bark millions of years ago, and slowly hardened into this warm, golden, half-transparent gem in which you can sometimes find, trapped forever, a mosquito or a single leaf from a forest that no longer exists anywhere on earth. The Greeks loved amber. They carved it into jewelry and into charms, and they called it by a word that you will recognize, even if you know no Greek at all. They called it electron. And from that word, from that yellow stone rubbed by Greek hands, comes our entire word for electricity. Every time you say electricity or electronics or electron, you are pronouncing, without knowing it, the ancient Greek name for a piece of fossilized tree resin. And why did this stone give its name to the greatest force of the modern world? Because of one small marvel that anyone can repeat at home, tonight, if they wanted to. If you rub a piece of amber with a woolen cloth, or against fur, the stone will suddenly begin to pull light things toward itself. Bits of dust, threads, small pieces of straw, dry blades of grass, a strand of hair. It draws them in as if by magic, as if the stone had woken up and grown hungry for tiny things. Rub a balloon in your hair, and the same thing happens. The balloon pulls the hairs and stands them on end. Rub a plastic pen against your sleeve and hold it near a small scrap of paper, and you will see the paper jump toward it. It is exactly the same phenomenon that amazed the Greeks 25 centuries ago. The same force waiting for you in any drawer in your house. Tradition gives the first real thought about this mystery to a man named Thales of Miletus, one of the 7 sages of ancient Greece, a man who lived around the year 600 before our era, and who is often called the first philosopher and the first scientist of the Western world. The story goes that Thales rubbed his amber, watched it draw in the little threads, and asked himself what kind of invisible force could be living inside a stone. He had no way to answer. He was missing 2,000 years of science. But he did the most important thing, which was to stop and ask why, instead of shrugging and going on with his day. It is worth saying that this story of Thales reaches us through much later writers, so it has something of a founding legend about it, one of those tales that civilizations tell themselves about their own beginnings. But true or half-true, it marks the starting point well. Electricity entered the human mind through the door of a yellow stone and a question with no answer. The ancients also knew another face of this force, far more brutal and bewildering, though they never suspected it was the same thing. In the Nile there lived, and there still lives, a fearsome fish that the Egyptians painted on the walls of their tombs more than 5,000 years ago. The electric catfish, a fish that could release a shock strong enough to numb the arm of anyone who touched it. The Egyptians called it, by some translations, the one who releases many, perhaps because its jolt made a person let go of whatever they were holding. And in the Mediterranean, the Greeks and the Romans knew the torpedo fish, a ray that produced similar shocks. Roman doctors, understanding nothing at all of the mechanism, actually used these shocks as a treatment. They would place the living fish on the head of a patient suffering from headaches, or over the aching joint of someone with gout, hoping the electric jolt would numb the pain. It was, in a strange way, the first electrical therapy in history. Thousands of years before anyone knew what an electron was, there is something quietly moving in imagining a Roman doctor, 2,000 years ago, with not the faintest idea of physics, carefully laying a living fish on the throbbing temple of a patient with a headache, and watching the shock genuinely take the edge off the pain. He was using medical electricity, the very same idea that hospitals apply today with astonishingly sophisticated machines, but with a river fish as his only technology. Nature had placed electricity within reach of the hand, quite literally, and the ancients touched it without ever understanding it. The way a child can turn on a light without knowing anything about power stations or magnets. Here it is worth stopping for a moment to take apart a story you may have heard, because this is the kind of story that prefers the comfortable legend, and we prefer the interesting truth. People sometimes speak of a so-called Baghdad battery, an ancient object that would prove that the civilizations of old Mesopotamia were already generating electricity. The story is real, at least as far as the object goes. In 1936, near the ancient city of Ctesiphon, in what is now Iraq, a clay pot about 2,000 years old was found containing a copper cylinder and an iron rod, sealed with bitumen. A German museum director suggested that this was a battery, an ancient cell, perhaps used to coat objects with a thin layer of gold or silver by electricity. The idea is seductive. It fits our appetite for ancient mysteries, and it has been repeated 1,000 times in sensational documentaries. The trouble is that the archaeologists, the people who actually study these things for a living, do not believe it. A respected archaeologist who traveled to Iraq to look into it put it plainly, saying she knew of no serious person in her field who thought that object was a battery. The more likely, and far more boring, explanation is that these pots were used to hold rolled-up scrolls or sacred texts, which decayed over time and left behind an acidic residue, and that the iron rod was not an electrode at all, but simply part of the seal. It is true that if you build a replica and pour acid into it, the setup can produce a tiny spark of electricity, but the fact that something can work as a battery does not mean, not even remotely, that it was ever built to be one. A lemon with 2 nails in it also produces electricity, and no one would say that nature invented the lemon to be a battery. The real story of the battery would have to wait another 2,000 years until an argument between 2 Italians and a pair of frog legs, and we will get there tonight. The first person to study all of this with something close to a modern scientific method was an English doctor named William Gilbert, around the year 1600, in the time of Queen Elizabeth of England, whose personal physician he was. Gilbert spent years experimenting patiently and rigorously with amber and with magnets, 2 phenomena that until then had been tangled together in the same cloud of superstition. And it was he who began to separate them, who realized that the pull of rubbed amber and the pull of a magnet were two different things, governed by different rules. Gilbert gathered his findings into a monumental book, considered one of the first great works of experimental science ever written, and in it he coined a new word, taken from the Greek name for amber. The property of drawing objects after being rubbed he called, in Latin, electricus, meaning in the manner of amber. And from there, a little later, came the English word electricity. And then the word in every language on earth. Gilbert spent a personal fortune on his experiments, the equivalent of buying 2 warships of his era, driven by pure curiosity. And he did one thing more. He proposed a bold and visionary idea that the earth itself is a giant magnet and that this is why compasses point north. He was right. With Gilbert, electricity and magnetism stopped being magic and stepped timidly into the world of science. But they were still only a curiosity for learned men, a game of stones that pull at bits of dust. And here it is worth pausing to think about something that becomes almost unbelievable once you sit with it. Between Thales of Miletus rubbing his amber around 600 before our era and the moment when humanity truly began to understand and to use electricity, more than 2,000 years went by. 2,000 years. For 20 centuries, generation after generation, empires that rose and fell, the static electricity of rubbed amber was little more than a parlor trick, a curiosity mentioned in passing in books that nobody knew what to do with. The Egyptians, the Greeks, the Romans, the entire medieval world, the Renaissance, all of them knew the marvel of amber, and none of them made anything of it, because the pieces of the puzzle were missing. What was missing was an understanding of charge. What was missing was the battery to give a steady current. What was missing were the magnets and the coils that would come later. Electricity lay sleeping in plain sight for 2 whole millennia, like a treasure buried beneath the feet of a civilization that walked over it without ever seeing it. And then, in barely 2 centuries, from the middle of the 1700s until now, all of it came loose, and that sleeping curiosity became the force that lit up the world. History sometimes moves like this: infinite patience, followed by a dizzying acceleration. For electricity to become a spectacle, a fashion, the sensation of an entire age, people had to learn to store it, to bottle it. And that happened all at once, and almost by accident, in a Dutch city in the middle of the 1700s, when a man very nearly died of fright. The city was Leiden, in Holland, and the year was 1745. For decades, the curious minds who played with electricity had entertained themselves with machines that generated charge by friction, contraptions with a glass sphere or cylinder that spun against a cloth and produced sparks and crackles. It was amusing but frustrating, because the electricity escaped the moment it was made. Like water running through your fingers, there was no way to keep it, to gather it up, to have it ready to use. And several investigators, almost at the same time and without knowing about one another, wondered whether electricity could be trapped inside a container, the way you keep water in a jug. One of them was Peter van Musschenbroek, a professor at the University of Leiden. Another was a German cleric named Ewald Georg von Kleist. The idea they tried was simple and wrong in its reasoning, but it worked wonderfully. They took a glass bottle, filled it with water, put a nail or a wire inside that came out through the stopper, and connected that wire to the electric machine to charge the water. The theory of the time said the water would hold the electricity the way a liquid holds anything else. And then, to check whether the bottle had charged, they made the mistake, or the lucky discovery, of holding the bottle in one hand while touching the wire with the other. The result was unforgettable. Von Kleist received a shock that numbed his whole arm and shoulder, and Musschenbroek, when his turn came, felt a jolt so violent that he later wrote, with a tremble you can still sense between the lines, that he had felt as if the world were ending, that his whole body had shaken as though struck by lightning, and that he would not repeat that experience even if he were offered the entire kingdom of France. A man who devoted his life to electricity, declaring that he would never do that again for anything in the world. That is how brutal the discovery was. That bottle, which came to be called the Leyden jar, after the city where it became famous, was the first device capable of storing electricity. The distant ancestor of every capacitor in every electronic device today. At last you could gather up charge, keep it, and release it all at once whenever you wished, in a powerful and controlled discharge. And that changed everything, because suddenly electricity stopped being a timid game of little sparks and became something able to deliver spectacular blows, to knock a person down, to make anyone who touched it jump. Overnight, electricity became a show. It is worth pausing on what that bottle really was, because how it worked contains an idea that will still be alive inside your phone tonight. The bottle did not hold the electricity in the water as they first believed. It held it in the glass itself, trapped between two conducting surfaces, the water or metal inside, and the hand or a metal foil outside, separated by the glass, which acts as an insulator. That arrangement, two conductors separated by an insulator, is what we call, today, a capacitor, and it can store electrical charge ready to be released in an instant. Every electronic device near you right now, your phone, your television, your computer, contains dozens or hundreds of capacitors, direct descendants of that Dutch bottle. The material has changed, the size has changed, they have become minuscule, but the idea is exactly the same one that frightened Muschenbroek half to death in 1745. Store electricity between two surfaces separated by an insulator and let it out when you need it. And what a show it became. The second half of the 1700s lived through a genuine electric fever. Traveling demonstrators moved through the drawing rooms of the European aristocracy, and for a few coins they left the guests open-mouthed with electric wonders. One of the most famous was the electric kiss. A young woman would be stood on a platform, insulated from the floor, and quietly charged with electricity by a machine until her whole body was full of it. Then a young suitor would be invited to kiss her, and in the instant their lips were about to touch, a crackling spark would leap between the two mouths and throw them apart, to the laughter and shrieks of the crowd. Desire, interrupted by a miniature lightning bolt. There were other tricks, just as astonishing for the time. A boy would be hung from silk cords charged with electricity, and sparks would leap from his hands and his face toward nearby objects, or he would be seen drawing scraps of paper to himself without touching them. Spirits would be set alight by bringing a spark down from the finger of an electrified person. And Benjamin Franklin, who took part in these amusements himself, once wrote that birds killed with electricity turned out to be uncommonly tender. Electricity was magic, it was science, it was theater, all at once, and all of Europe wanted to see it. But the most astonishing spectacle of all, the most outlandish and the most important one for our story, was staged by a French abbot named Jean-Antoine Nollet, who besides being a clergyman was a serious physicist and the great electrical showman of his time. Nollet wanted to answer a real question, not merely to entertain. He wanted to know how fast electricity travels. Is it instant? Does it take time to run down a wire? And to find out, he devised an experiment of a scale bordering on the absurd. The kind that only occurs to someone with access to a great many people willing to help. He gathered around 200 Carthusian monks from a monastery and arranged them in a line that formed an enormous circle, each monk joined to the next by a length of iron wire that both of them held in their hands. The complete circle of monks and wires stretched almost a mile long. A human serpent, 200 robed men holding hands through cables, wrapped around the monastery. And then, without warning, Nollet connected the ends of the circle to a battery of well-charged Leyden jars, and discharged all the electricity through the chain of monks at once. The result was one of the most extraordinary images in the history of science. The 200 monks leapt and cried out, all of them together, in the same instant, like a single creature nearly a mile long, seized by a single simultaneous spasm. Nollet, watching from outside, could see no delay at all between the first monk and the last. They all seemed to jump at the very same moment, and from this he concluded, rightly for what his instruments could measure, that electricity travels at an enormous speed, almost instantaneous, impossible to time with the means of his era. He was so delighted with the experiment that he repeated it before the king himself, Louis XV, this time with a company of nearly 200 royal guards holding hands, who also leapt as one before the amused and horrified court. Imagine the scene in the palace, the courtiers in their wigs and their silks holding back their laughter, and then, suddenly, nearly 200 hardened soldiers giving a start and a shout in unison, like puppets moved by the same invisible thread. Electricity had become the most exclusive and sophisticated entertainment in Europe, able to astonish kings. Nolit, by the way, would have a curious part to play in our story, because he became one of Franklin's great rivals. When the American's ideas about electricity and his experiments with lightning began to triumph in Europe, the abbot Nolit, who had his own competing theories, resisted with tooth and nail, wounded in his pride as the great electrical authority of France. He even came to suspect that this fellow Franklin did not really exist, that he was an invention of his enemies, dreamed up to overshadow him. But the weight of the evidence won out in the end, and Franklin's ideas, simpler and more accurate, prevailed over the abbot's. It is one of those rivalries in the history of science in which the newcomer, from a distant colony, defeats the great established sage of the mother country, not with authority and not with titles, but simply because he was right. Nature pays no attention to hierarchies or to national pride. In the end, the one who is correct always wins. Those leaping monks, without knowing it, had demonstrated something profound, something it would take us almost 2 centuries to fully understand, and one of the most counterintuitive things in all of electricity. The electrical signal, the push, travels down the wire at nearly the speed of light, so fast that the monks all jump together. And yet, as we will see later tonight, the electrons that make up that current, the particles that actually move inside the wire, crawl along at the pace of a tortoise, slower than a snail. That paradox, a lightning-fast signal made of terribly slow particles, was already hidden in the jump of Nolit's monks, waiting patiently for someone to understand it. But that was still far off. For now, in the middle of the 1700s, electricity was an astonishing force that could be kept in bottles and could make monks leap, but whose deepest nature remained a total mystery. Nobody knew what it was, until a remarkable man in the British colonies of America had the audacity to look up at the sky during a storm, and to wonder whether those giant flashes of lightning might not be, at bottom, the very same spark that leapt between the lips of the electric kiss, only millions of times larger. That man was Benjamin Franklin, and he is one of the most complete figures history has ever produced. Today we remember him mostly as one of the founding fathers of the United States, one of the signers of its Declaration of Independence, a diplomat and a politician. His face is on the $100 bill. But before all of that, Franklin was a printer, a writer, a tireless inventor, and one of the most brilliant scientists of his time. He invented bifocal glasses, a more efficient stove, and a musical instrument made of glass bowls, for which both Mozart and Beethoven would later compose pieces. And he refused, on principle, to patent his inventions, because he believed they should benefit everyone freely. And in the middle of that overflowing life, he found the time to become obsessed with electricity, and to have an intuition that struck almost all of his contemporaries as madness. The intuition that lightning, the bolt that falls from the sky in a storm, was not a divine manifestation, and not a separate phenomenon, but simply electricity. The same electricity of the Leyden jar and the electric kiss, only on a colossal scale. Think about it from within his own era, and you will see how bold the idea was. On one hand, you have a little spark that leaps between 2 lips in a drawing room. On the other, you have a bolt able to split a tree in 2, to set a church on fire, to kill a man. To say they are the same thing, differing only in size, was like saying the flame of a candle and the burning of an entire forest are the same fire. Today it seems obvious. Back then it was an extraordinary claim. And Franklin, who was above all a practical man, did not settle for speculating. He designed experiments to prove it. His idea was to capture a little of the electricity of a storm, and to show that it behaved just like the electricity of the laboratory. Here we reach the famous story of the kite, which is worth telling carefully, separating what really happened from what legend has since embroidered onto it. The popular image is of Franklin flying a kite in the middle of a storm and being struck by a bolt of lightning that runs down the string, which is a beautiful image and completely false. Because if a bolt had struck his kite, Franklin would have died on the spot, the way poor Richmond died in Saint Petersburg. What Franklin proposed, and probably did, in 1752, was something more subtle. The idea was to fly a kite up toward a storm cloud, not so that lightning would strike it, but to gather the diffuse electric charge that fills the air during a storm, much gentler than a direct bolt. That charge would come down the damp string of the kite, which conducts electricity until it reached a metal key tied at the end, and from that key, Franklin could draw small sparks with his knuckle and charge a Leyden jar with them, proving that the electricity of the sky and the electricity of the laboratory were one and the same. Curiously, the experiment that first truly proved his theory was not carried out by Franklin, but by French scientists who followed his published instructions. A few weeks before the supposed feat of the kite, in a village in France, they set up a tall, insulated iron rod, according to Franklin's design. They waited for a storm to pass, and they managed to draw sparks from the rod, confirming that yes, the clouds were charged with electricity. The Americans' idea was correct, and Europe celebrated it. The kite story reaches us mostly through an account Franklin gave a friend years later, and some serious historians doubt even the details, or whether it happened exactly as told. But the core is solid, and that is what matters. Franklin proved, or helped to prove, that lightning is electricity, and that demonstration had an immense practical consequence, one that saved and still saves countless lives. Because if lightning is electricity, and electricity always seeks the easiest path to the ground, then you can offer it a path on purpose, a safe path, so the bolt comes down where we want it to, and not where it would do harm. This is how the lightning rod was born. A simple pointed metal bar, placed at the very top of a building, connected by a thick cable all the way down into the earth. When a bolt threatens, it prefers to jump to that metal point and come down calmly along the cable and bury itself in the ground, rather than tear through the roof, the beams, and the people. Franklin's lightning rod spread across the whole world with astonishing speed for the era, and began to protect houses, churches, and powder magazines that used to burn with every storm. It was one of the first times in history that a scientific discovery translated directly and visibly into human lives saved. Science coming down from the sky never was the phrase more fitting to protect ordinary people, and not everyone welcomed it with joy, which says a great deal about that era and also about our own. There were those who opposed the lightning rod on religious grounds, arguing that lightning was an instrument of the divine will, a punishment or a warning from heaven, and that to divert it with a bar of metal was an impiety, an arrogant attempt to cheat the designs of God. It was especially tragic that churches, with their high bell towers, were among the buildings most often struck by lightning, and that for centuries a good number of bell ringers died while ringing the bells during storms, precisely in the hope of driving the bad weather away with their blessed sound. Franklin's lightning rod, that humble bar of iron, saved more bell towers and more lives than whole centuries of prayer. And little by little, even the most reluctant ended up placing one on their churches. It was a small and quiet victory of the observation of nature over ancient fear. One of many in this story, Franklin, a practical man with a good sense of humor, did not throw himself too far into these quarrels. It was enough for him that it worked. Franklin also did something that still affects each of us every single day, though almost nobody knows it, and it carries a delicious irony. To explain electricity, he proposed that it was a single invisible fluid that could be present in excess or in shortage in different objects. Objects with an excess of fluid he called positive, with a plus sign. Objects with a shortage, negative, with a minus sign. And he decided by pure convention that electric current flowed from positive to negative, from the plus to the minus, the way water falls from where there is a lot to where there is little. It was a reasonable choice, an elegant one, and it turned out to be wrong. Because when, more than a century later, it was discovered what the particles that actually move in a metal wire really are, it turned out they were electrons, and electrons carry a negative charge, and they flow the exact opposite way from what Franklin had supposed, from the minus to the plus. But by then, Franklin's convention had been settled for so long, in every book, every formula, every piece of engineering, that nobody wanted to change it. And so even today, in every school and every university in the world, students are taught that conventional current runs from plus to minus, in the opposite direction from the way the electrons actually move. Every engineer on the planet works, every day, with an arrow that points backwards, because of a reasonable decision made by a printer from Philadelphia in the 1700s. The history of science is full of these curious inheritances, these little scars from the past that we carry along out of sheer convenience. With Franklin, electricity was no longer just a drawing room game. It was a phenomenon of nature, as vast as a storm, that could be understood and even tamed a little. But it was still, in essence, spark and discharge, something abrupt, momentary, a flash, and then it was gone. Nobody had yet managed a sustained electric current, a continuous, gentle flow that you could keep running for as long as you liked. And that leap, one of the most important in all of history, did not come from a storm. And it did not come from a machine. It came from the leg of a dead frog hanging from a hook, and it set off one of the most famous and most fruitful scientific quarrels ever recorded. We are in Bologna, in Italy, in the 1780s. Luigi Galvani is a respected doctor and anatomist, a methodical and religious man, married to Lucia, the daughter of his own teacher, who works at his side in the laboratory and is his great intellectual companion. Galvani studies the anatomy of frogs, and in particular their legs, which he dissects and prepares with care, hanging them from hooks. And one day, almost by chance, he observes something that leaves him stunned. A dead frog's leg, completely dead, separated from the body of the animal, contracts all at once. It gives a jolt, as if it were alive, when he touches it with metal, in certain circumstances. At first it happens near one of those electrical machines that threw off sparks. But then Galvani discovers something even more unsettling. He hangs the frog legs from brass hooks on the iron railing of his balcony, and he sees them twitch on their own, with no machine anywhere near. Simply from the leg making contact with two different metals, the brass of the hook and the iron of the railing. For Galvani, the conclusion is astonishing and beautiful. He believes he has discovered the secret of life itself. He thinks that inside the muscles and nerves of the animal there resides a fluid of its own, an animal electricity, a vital force of an electrical nature. That makes the muscles move, and that may be the very principle of life. The leg moves, he reasons, because the metal releases that electricity stored in the tissue, the way a Leyden jar is discharged. The living body, in his vision, would be a kind of animated battery, charged with vital electricity. Galvani publishes his experiments in 1791, and the idea causes a sensation across all of Europe. Animal electricity, the spark of life, is a powerful idea, almost a poetic one, and it will have an immense cultural descendants, as we will see in a moment. But there was another man watching, a brilliant physicist from the nearby University of Pavia, named Alessandro Volta. At first Volta was fascinated and accepted Galvani's conclusions. But he was a rigorous physicist, and the more he repeated the experiments, the more an uncomfortable suspicion circled his mind. What if the electricity did not come from the animal? What if the frog tissue was not the source, but simply the detector? Volta noticed a detail that had seemed secondary to Galvani, the fact that the most reliable contractions happened when the leg touched two different metals at once, like brass and iron. And he formulated a rival hypothesis, far less romantic, but, as it would turn out, more profound. The electricity, Volta proposed, is not produced by the frog. It is produced by the two different metals when they touch through a moist medium. The frog's leg is not a living battery. It is only a wet cable, and a very sensitive meter that twitches when the current the metals generate passes through it. The spark is not in the life. It is in the meeting of two metals. The dispute between Galvani and Volta became one of the most famous in the history of science. Two honest and brilliant men defending opposite interpretations of the same facts. And to prove that he was right, to prove that two different metals separated by a moist medium generate electricity with no need of any animal, Volta did something brilliant. In the year 1800, he built a device that stacked, one on top of another, discs of two different metals, zinc and copper, separated by pieces of cardboard or cloth soaked in salt water. Zinc, copper, wet cloth. Zinc, copper, wet cloth. Over and over, forming a column. And from the ends of that column, with no frogs, no animals, no vital force at all, flowed a steady electric current, continuous, stable, that did not exhaust itself in a single flash like the Leyden jars, but flowed on and on for as long as the setup held together. That was the first battery in history, the voltaic pile, and its importance is almost impossible to overstate, because for the first time humanity had a source of continuous, controllable electric current. Until then, all electricity had been spark, discharge, an instant, and then it was over. With Volta's pile, you could have current flowing for hours, a gentle, constant electric river that scientists could use to experiment calmly, to pass current through substances, through liquids, through gases, and see what happened. The pile threw the doors wide open to everything that would come after. Volta presented his invention in a letter to the Royal Society of London in the year 1800, and it caused such a sensation that Napoleon himself, fascinated, summoned him to Paris to give a demonstration, showered him with honors and money, and granted him a medal and a title of nobility. One of the most powerful men in history, at the very peak of his military glory, bowing before an Italian professor and his column of wet discs. That is how immediately the world understood what this was. In a sense, every battery you have ever used in your life, the one in your phone, the one in your car, the batteries in the remote control, is a direct descendant of that column of zinc and copper discs with wet cloth that Volta stacked up in Pavia. The word pile, in fact, comes literally from that, from the fact that it was a pile, a heap of things stacked up. And the unit we use today to measure voltage, the volt, carries his name in his honor. Every time you read that a battery is 12 volts, you are naming Alessandro Volta. All modern batteries, however sophisticated, still work on the same essential principle Volta discovered. Two different materials separated by a substance that lets charges pass so that a chemical reaction pushes electrons from one side to the other and generates current. The materials have changed. They have grown lighter, more powerful, rechargeable, but the heart is still the heart of Volta's pile. When your phone lasts all day on one charge, you owe the favor, in the last analysis, to an argument about frog legs that took place in Italy more than 2 centuries ago. And so who was right, Galvani or Volta? This is one of those lovely occasions when science answers, both of them. Volta was right about the essential point of the dispute. The current in those experiments came from the contact of the metals, not from a mysterious vital force, and his pile proved it beyond doubt. But Galvani was also right about something deep. something Volta, in his victory, dismissed too quickly. Because there is genuine electricity in living things. Nerves do transmit electrical signals. Muscles do move by electrical impulses. Your heart is beating right now thanks to an electric spark that repeats. Galvani was wrong in the details and in the name. There was no special, separate animal electricity. It was the same electricity as everything else. But he was right in the greater intuition that life and electricity are intertwined in an intimate and essential way. Volta won the battle of the laboratory. Galvani, in the long run, won the battle of the human body. And to that electricity of life, the one that runs through your nerves and makes your heart beat, we will devote a good while later tonight, because it is one of the most astonishing things there is. First, though, we have to tell the chilling and fascinating episode in which Galvani's animal electricity stepped out of the laboratory and into the realm of the macabre, when a nephew of his began to apply current to human corpses in front of horrified audiences and without meaning to, gave rise to one of the most powerful myths of modern culture. The story of Frankenstein. The nephew was named Giovanni Aldini, and he was a man of showmanship as much as of science. Convinced that his uncle's animal electricity concealed important truths, and perhaps also drawn by the fame those demonstrations brought, Aldini began to travel across Europe, applying electric current to the corpses of animals, and increasingly of people, in front of crowds that gathered somewhere between horror and fascination. His most famous demonstration took place in London in January of 1803. The authorities handed him the freshly executed body of a murderer, a man named George Forster, who had just been hanged at Newgate Prison for drowning his wife and daughter. The body had hung for an hour in the cold of a London winter when Aldini laid it on his table and connected the cables of a powerful pile. What happened next was recorded in the accounts of the time, and it chills the blood even today. When Aldini applied the electrodes to the face of the corpse, the jaw of the dead man began to tremble. The muscles of the face twisted into ghastly grimaces, and one of the eyes opened. When he applied the current to other parts of the body, a fist clenched and rose. The legs kicked. The back arched. To the eyes of the spectators, it was as if the hanged murderer were coming back to life on the table, writhing and gesturing, moved by an invisible force. The effect was so overwhelming that, as the story goes, one of the official attendants was so traumatized by what he had seen that he died shortly afterward. It was said, from the pure shock. Aldini insisted that his purpose was not to resurrect anyone, but to investigate whether electricity might serve to revive people who had recently drowned or suffocated. An idea that, at bottom, was not absurd and that points, faintly, toward modern resuscitation. In those days there already existed societies devoted to trying to revive the drowned, who were many in cities beside rivers. And all sorts of methods were tried, blowing in air, giving warmth, rubbing the body. And some pioneers thought that electricity, that force which made the muscles of the dead leap, might have a role there. They were not entirely off track, though real resuscitation would take more than a century to develop. But for the public, the spectacle was something else. It was life and death, fighting over a body, blow by electric blow. People paid to see it, with the same mixture of horror and fascination with which we watch a horror film today. And they left there shaken, talking for days about the eyes that opened and the fists that clenched, wondering where exactly the border lay between being alive and being dead, if a corpse could move like that. These macabre demonstrations, these corpses that moved as the current passed through them, saturated the cultural air of the era, and very particularly the imagination of a young English writer. Her name was Mary Shelley, and in 1818, at barely 20 years old, she published a novel that would become one of the most enduring myths of humanity, Frankenstein, or the modern Prometheus. The story of a scientist who, playing at being God, assembles a body from the parts of corpses and breathes life into it by means of a mysterious force. Mary Shelley knew of the experiments in galvanism. She had heard of Aldini, of the frog legs, of the corpses shuddering with the current, and all that atmosphere of electricity and death and reanimation beats in the heart of her novel. Although the book does not describe the method in detail, popular culture soon associated Frankenstein's creature forever with electricity, with the bolt of lightning that comes down from the sky and gives the monster life, that image we all carry in our heads. And so an argument about frog legs and baloney ended up, barely a generation later, giving birth to the modern myth of the human being who steals from nature the secret of life and creates a monster. Electricity was no longer only science. It had become a symbol, a metaphor for the power and the danger of playing with the fundamental forces of the universe. Let us come back now from the realm of the macabre to the laboratory, because Volta's pile, that column of discs and wet cloth, was about to become the most powerful tool in the science of the early 1800s, in the hands of an English chemist as brilliant as he was charismatic. His name was Humphrey Davy, and he was a star. Born in a village in Cornwall, the son of a humble family, an apprentice to an apothecary, Davy rose by pure talent to become the most famous scientist in England, able to fill lecture halls with an audience that included ladies of high society, who came as much for the science as for the charm of the young lecturer. Davy had a reckless, experimental streak that bordered on the insane. He discovered the effects of laughing gas, nitrous oxide, by inhaling it himself, repeatedly, to the point of becoming somewhat addicted to its euphoric effects, decades before anyone thought to use it as an anesthetic in operations. He held evenings in which his friends, poets and thinkers, inhaled the gas and afterward described their visions and their uncontrollable laughter, and he himself, in the middle of a high, wrote down that the universe was made of ideas and sensations. It was a pity that neither he nor anyone else in his era took the obvious step, to use that gas which dulled pain to operate without suffering, something that would have spared unspeakable agonies to several generations of patients. Anesthesia would still take almost half a century to arrive, though the laughing gas that made it possible was already laughing in Davy's laboratory. In a laboratory accident, playing with other substances, he nearly lost his sight, and in his later years he dragged along a health broken by so many experiments upon himself. But his great feat he accomplished with the pile. Davy built giant voltaic piles with hundreds of plates, the largest of his era, and with them he passed powerful currents through molten and dissolved substances. In a process we now call electrolysis, breaking substances apart with electricity. And in doing so, he began to discover new chemical elements that no one had ever seen in a pure state, because they were so strongly bound to others that only the brute force of the electric current could separate them. In barely a couple of years, Davy isolated, for the first time, potassium, sodium, calcium, magnesium, barium, and other elements, tearing them out of their compounds with electricity. It was as if the pile were a master key, able to open chemical locks that had been shut since the beginning of the world. Davy also created one of the first powerful electric lights, the arc lamp, by making the current jump between two rods of carbon with a blinding flash. A distant foretaste of the electric lighting that would still take decades to reach the streets. And yet, great as all these achievements were, it is often said that the greatest discovery of Humphrey Davy was not a chemical element and not a lamp, but a person, a poor young man with almost no formal schooling who showed up before him one day with an unusual gift, humbly asking for a job. Any job, as long as it let him devote himself to science. That young man was named Michael Faraday, and he was destined to surpass his master and to become one of the greatest geniuses in the history of humanity. The life of Michael Faraday is one of those stories that seem invented, too beautiful to be real, and yet are true. He was born in 1791 in a poor neighborhood in the south of London, the son of a sickly blacksmith who often could not work, in a family that sometimes did not have enough to eat. Faraday received the barest education, barely reading, writing, and the 4 operations of arithmetic. He did not go to university. He learned almost no mathematics, and that lack would follow him all his life. By his origin and his era, he was destined for a manual trade and an obscure life like millions of people before and after him. At 14, he became an apprentice at a bookbindery, a workshop where books were sewn and covered, and there, among the pages of the books he was binding, the miracle happened. Faraday did not merely bind the books, he read them. He devoured everything that fell into his hands, and above all he fell in love with books of science, with articles about chemistry and about that new and marvelous force, electricity, he read at night after the workday. He carried out his own experiments with scrap materials. He took exquisite notes. A customer of the shop, seeing the young man's passion, gave him tickets to attend the public lectures of Humphrey Davy at the Royal Institution of London, the very ones that filled halls with aristocrats. Faraday attended, spellbound, took detailed notes of everything Davy said, and then did something that reveals who he was. He bound his own notes of the lectures with the care of a master craftsman, forming a small and beautiful book, and sent it to Davy along with a letter asking, with all humility, for a job, any job, so long as it let him work in science. Imagine the scene, the most famous chemist in England, receiving from the hands of an unknown and poor bookbinder an exquisite book made out of his own words. Davy was impressed, and a little while later, when he needed a laboratory assistant, he remembered the young man. In 1813, Faraday entered the Royal Institution as an assistant. He had crossed, in an impossible single leap, the border that separated poverty from science. What came after was the rise of one of the greatest experimental talents in history. Faraday had a prodigious physical intuition, an almost magical ability to imagine how things worked on the inside, which more than made up for his lack of mathematics. And he had, besides, a character that makes him dear to us across the centuries. Faraday was deeply humble by conviction and by faith. He belonged to a small and very strict Christian community, the Sandemanians, which preached simplicity, detachment from riches, and a rejection of vanity. And Faraday lived by that until the end. He refused to be made a knight, to be made a sir, because he wanted no worldly titles or honors. He refused, not once but twice, the presidency of the Royal Society, the highest scientific honor in his country, when the British government asked him to develop chemical weapons, poison gases for the Crimean War. He refused on moral grounds, saying it was technically possible, but that he would not take part. He lived modestly, gave free lectures for children that became legendary, and when he died, he refused to be buried in Westminster Abbey, the pantheon of the kings and the great men of England, where Newton lies. He preferred a simple grave in an ordinary cemetery. In an age that was beginning to worship money and fame, Faraday was a man who had both within his reach and turned them down on principle. There is one detail of his life that portrays him entirely, and it is the Christmas lectures for children that he founded at the Royal Institution, and that, incredibly, are still held today, almost 2 centuries later. Faraday, who had come to science as a poor child because someone gave him tickets to a lecture, wanted to give that gift back to the world, and devoted part of his energy to explaining science to the youngest, in a way that was simple, astonishing, and free. His series of talks on the chemical history of a candle, in which he took the humblest object imaginable, a single burning candle, and from it explained half the chemistry and half the physics of the universe, is considered a jewel of scientific popularization for all time. That man, who had changed the world with his magnets, would kneel, metaphorically, before a room full of children, to light in them the same spark of curiosity that had once saved him from a life of poverty and darkness. And perhaps that is the most beautiful image of Faraday, not the genius in his laboratory, but the humble man who knew that knowledge only has meaning if it is given away, if it is passed from hand to hand, from generation to generation. Like a flame that lights another flame without ever going out itself. But let us turn to the science, because what Faraday discovered changed the world more than almost anything else in history. To understand it, we have to go back a little, to an accidental discovery that had taken place in Denmark in 1820. A professor named Hans Christian Ørsted was giving a class, doing a demonstration with a pile and a wire, when he noticed something he did not expect. Near the wire through which the current was flowing, there happened to be a compass, and Ørsted saw that when the current passed through the wire, the needle of the compass moved. It swung away from its position as if pushed by an invisible force. When he cut the current, the needle went back to its place. That was astonishing, and it was a clue to something enormous. A compass is a magnet. It responds to magnetism. For an electric current to move a compass meant that electricity and magnetism, two forces that until then had been believed completely separate, were secretly connected. An electric current, as it flows, creates around itself a magnetic field, an invisible magnetism that wraps around the wire and can move a compass. Electricity and magnetism were somehow two faces of the same coin. This discovery electrified, never was the word more fitting, the scientists of all Europe. And Faraday was fascinated. Ørsted had shown that electricity produces magnetism, and Faraday, with that intuition of his for the symmetries of nature, asked himself the reverse question, the brilliant question. If electricity creates magnetism, should magnetism not be able to create electricity? If a current moves a magnet, could a magnet not, somehow, generate a current? The idea circled him for years, and in 1831, after many attempts, he found the answer, and it was an answer that would quite literally light up the entire world. What Faraday discovered that year is, without exaggeration, one of the most important findings in the history of humanity, even though almost nobody knows his name. It is called electromagnetic induction, and it sounds complicated, but the idea is of a luminous simplicity. Faraday discovered that a magnet in motion generates electricity, that if you move a magnet near a wire, or move a wire near a magnet, a current appears in the wire, arising out of nothing, created by the simple movement. You need no pile, no chemical reaction, no light and jar, only a magnet, a wire, and movement between them. Movement turns into electricity. Stop for a moment and savor this, because it is the secret key to your entire modern life. In one of his experiments, Faraday took a copper disc and spun it between the poles of a horseshoe magnet, and as the disc turned, a continuous electric current flowed out of it. He had built the first electric generator in history, the first dynamo, a device that turns motion into electricity. It is worth imagining the scene, because it has a moving simplicity to it. A man alone in a basement in London, moving a magnet beside a coil of wire, watching how the needle of his meter swung aside just at the instant of the movement and returned to zero when the movement stopped. Current was only generated during the change. During the movement, a still magnet beside a still coil produced nothing, however powerful the magnet. It took the gesture, the movement, the change. That detail, that only movement generates electricity, that nature charges for the change and not for mere presence, is the heart of everything. Faraday understood it that year, and with it, without fully knowing it. He had just invented the way in which humanity would manufacture nearly all of its electricity forever. Think about it. If you have something that spins, anything at all, and you connect it to this principle, you get electricity. And it turns out that in the world there are a great many things that can be made to spin. Falling water from a river can spin a wheel. Boiling steam can push a turbine and make it spin. Wind can spin a set of blades. And each of those spins, thanks to Faraday's discovery, can be transformed into electricity. Almost all the electricity you use in your life, the one that lights this screen, the one that illuminates your house, the one that charges your phone, is born exactly like that, from the principle Faraday discovered in 1831. It is born from spinning a magnet or a coil near another. We will come back to this, because it is so important that it deserves to be understood completely. But hold on already to the idea, because it is beautiful in its simplicity. The entire electric civilization rests upon a gesture as simple as spinning a magnet. Faraday did not stop there. He also did the reverse process and built one of the first electric motors, a device that does exactly the opposite of the dynamo. The dynamo turns movement into electricity. The motor turns electricity into movement. You feed it current, and it spins. And that is the other pillar of your world. Every fan, every washing machine, every electric train, every electric car, every hard drive, every elevator works with an electric motor that is, in essence, the grandchild of that first contraption of Faraday's. The dynamo and the motor generating electricity with movement and generating movement with electricity are the two turns of the same key. And that key, together with Arsted's understanding and Faraday's, opens absolutely the entire technological world you live in. Faraday also contributed a profound conceptual idea, one that his more mathematical colleagues looked at, in his time, with disdain, and that turned out to be one of the most brilliant intuitions in physics. Faraday knew almost no mathematics, so he did not think in formulas. He thought in images, and to understand how a magnet could influence another at a distance, or a wire, without touching it, he imagined that the space around a magnet or an electric charge is not empty, but full of something invisible, lines of force that stretch out through space and carry the influence. Imagine the curved lines that iron filings draw when you scatter them over a sheet of paper with a magnet underneath, those arcs that run from one pole to the other. Faraday thought those lines were real, that the space around the magnet was genuinely modified, tense, full of an influence that he called a field. The concept of the field, that idea that empty space can be full of invisible forces, was born from the imagination, without mathematics, of a self-taught bookbinder, and today it is one of the pillars of all modern physics. Fields are everywhere in the science of our time. The electric field, the magnetic field, the gravitational field, and even the quantum fields that particles are made of, all of them descend, in one way or another, from the lines of force that Faraday imagined while looking at iron filings. There is a lovely anecdote told about Faraday, though it is worth warning that its authenticity is doubtful, and it is probably one of those stories that improve with time. It is said that an important politician, a minister of finance, visited his laboratory, and on seeing all those experiments with magnets and wires that produced nothing useful yet, asked him, with a certain contempt, what all of it was good for. And Faraday, so the legend goes, replied, "Sir, of what use is a newborn baby?" Meaning that a discovery in its infancy, however useless it may seem, can grow until it transforms the world. Another version has him answering, "Sir, one day you will be able to tax it." True or not, the anecdote captures a deep truth. When Faraday played with his magnets and his coils, it looked like a laboratory curiosity with no application at all. Nobody, not even Faraday himself, could imagine that from those games would come, barely half a century later, the complete electrification of the planet. The illuminated cities, the industry moved by motors, and, ultimately, the whole electric and electronic civilization you live in today. Faraday's newborn baby grew up to become the modern world. But for that baby to grow, for Faraday's intuitions to become a complete and precise theory, someone was needed who could translate those images of lines of force into the rigorous language of mathematics. Faraday saw the film. What was missing was the one who would write the score, and that someone was a young Scotsman, quiet and brilliant, who was going to achieve one of the greatest intellectual feats of all time, to unite, in a handful of equations, electricity, magnetism, and, to everyone's amazement, light. Before we get to the Scotsman, it is worth stopping a moment on the first useful things humanity built with the connection between electricity and magnetism that Arsted and Faraday had uncovered. because they changed the world even before anyone fully understood why they worked. The first was the electromagnet, and it is of an almost magical simplicity. If an electric current creates a magnetic field around itself, as Ørsted saw, then all you need to do is coil a wire into many turns, a coil, to add up the effect of all those turns and get a powerful magnet. And the wonderful thing is that this magnet turns on and off at will, simply by connecting or cutting the current. A magnet with a switch. You put a piece of iron inside the coil to strengthen it, you give it current, and you have a magnet able to lift heavy objects. You cut the current, and it stops being a magnet and drops what it was holding. Those giant electromagnets are the ones you see in scrapyards, lifting whole cars and dropping them wherever they want, and they sit at the heart of countless machines, from doorbells to the trains that levitate over magnetic rails. But the application that truly transformed the world in the 19th century, even before the electric light, was the telegraph. The idea was beautiful in its simplicity. If you stretch a very long wire between two cities and put a pile at one end and an electromagnet at the other, then every time you close the circuit at your end, the electromagnet on the other side is activated instantly and pulls a little metal piece that makes a click. You open and close the circuit with a button, and hundreds of miles away a series of click sounds, reproducing your rhythm exactly. By combining short and long clicks, dots and dashes, you can encode any letter of the alphabet, and so send words, sentences, whole messages at the speed of electricity, that is, almost instantly, across distances that used to take days or weeks to cover on horseback. It was a revolution as deep as the internet would later be. For the first time in history, information could travel much faster than any messenger, any horse, any ship. A piece of news that once took weeks to cross a continent began to cross it in seconds. Wires were laid across the land, and then, in an astonishing feat of engineering, wires were laid across the bottom of the ocean, joining whole continents, so that Europe and America could at last converse in nearly real time. The world suddenly became smaller, and all of it, that first nervous system of the planet, ran on the humble connection between a current and a magnet that Ørsted had discovered by chance, watching a compass tremble in a class. Think of the chain of events. A Danish professor notices, almost by accident, that a compass moves near a wire with current. From that minor observation comes the idea that electricity and magnetism are connected. From that idea comes the electromagnet. From the electromagnet comes the telegraph. From the telegraph comes the first worldwide network of instant communication, and all of it in barely a few decades. It is a perfect example of how apparently useless science, the mere curiosity of why a needle moves, ends up giving birth to technologies that transform civilization. Faraday's newborn baby once again growing up fast. And the greatest thing was still missing, because this whole relationship between electricity and magnetism, which already gave magnets with switches and messages crossing oceans, hid within itself an even deeper secret, a secret about the very nature of light, that only a mind able to translate Faraday's images into equations could reveal. And that mind was already at work in Scotland. Before we meet that Scotsman, let us take a pause in the story and spend a while understanding, truly and calmly, what electricity is on the inside. And if you have just drifted for a moment, or lost the thread a little among so many characters, do not worry, this is a good time to pick it back up. So far we have seen the great human adventure, how the Greeks rubbed amber without understanding it, how we learned to store electricity in bottles, how Franklin tied the lightning of the sky to the science of the laboratory, how Galvani and Volta argued over a pair of frog legs, and out of that argument came the first battery, and how Faraday, the poor boy, discovered that a magnet in motion creates electricity, the secret that holds up the modern world. All of that was the history, the characters, the human drama. Now comes the other half, understanding what this invisible thing truly is, And you will not need a single formula. Only a little imagination and the willingness to let yourself be carried. Because until now we have seen what electricity does, the sparks, the discharges, the currents, but we have not opened the box to see what it is made of. And for that we have to travel to the interior of matter, to a scale so small it defies imagination, the world of atoms. Everything around you, this screen, the air, your own hand, is made of atoms. Tiny pieces so small that on the head of a pin there fit more atoms than there are stars in the Milky Way. And each atom in turn is made of even smaller pieces. At the center it has a dense, heavy nucleus where particles called protons live, and around the nucleus, in a kind of diffuse cloud, flit other, far lighter particles called electrons. Protons and electrons have a strange property, a quality that nature gave them, and that is the origin of all the electricity in the universe. That property is called electric charge. Protons have a positive charge, electrons have a negative charge, and the rule of the game, the golden rule of all electricity, is simple, and you know it from magnets. Like charges repel, opposite charges attract. Two positive charges push apart. Two negatives push apart. A positive and a negative seek each other, attract each other. In a normal, calm atom, there are the same number of positive protons as negative electrons, and their charges balance exactly. They cancel out, so that the whole atom is neutral, neither positive nor negative, and that is why the world in general seems electrically calm, because almost all matter is balanced, its positive and negative charges evened out. Electricity appears when that balance is broken, when, for some reason, some electrons separate from their atoms and gather in one place, or go missing from another. An object with extra electrons ends up negatively charged. An object short on electrons ends up positively charged, and then those unbalanced charges begin to push and pull at one another, wanting to rebalance. And in that longing lies all of electricity, from the smallest spark to the most colossal bolt of lightning. Now we finally understand the mystery of the Greek's amber, that yellow stone from the beginning of our story. When you rub amber with wool or a balloon with your hair, what happens is that the rubbing tears electrons off one material and deposits them on the other. One of the two is left with extra electrons, and the other short of them, and so one ends up negatively charged and the other positively. That is why rubbed amber attracts bits of dust, because its unbalanced charge pulls on the small charges of light objects. That is why a rubbed balloon stands your hairs on end, because the hairs, charged the same as the balloon, repel one another and spread apart, trying to get away from each other. And that is why, on a dry day, when you take off a wool sweater, you hear little sparks crackle. Or when you touch a door handle after shuffling your feet across a carpet, you get a small shock. In all those cases, you have separated electrons by rubbing. You have gathered charge, and that charge leaps all at once, seeking to rebalance. It is exactly the same phenomenon Thales observed 25 centuries ago, and now we know its name and its mechanism. It is called the triboelectric effect, the electricity of friction, and you produce it, without meaning to, dozens of times a day. And why do these sparks and small shocks happen so much more in winter or on dry days, and almost never in summer or in humid weather? Here there is a lovely detail. Humid air, full of water vapor, is a little bit conductive, and it quietly discharges, bit by bit. The charge you gather, before enough of it can pile up to give a spark. But the dry air of winter, or the air of heated rooms, is a much better insulator. So the charge accumulates on you without escaping. It keeps building up as you move, shuffle your feet, rub against your clothes, until it reaches a surprisingly high voltage, sometimes thousands of volts. And then, when you bring your finger near a piece of metal, it leaps all at once in that dry, crackling shock. It may seem alarming that your body could gather thousands of volts, but remember the difference between voltage and current, which we will see in a moment. It is a lot of pressure, but a very small amount, so it only gives you an annoying pinch, nothing dangerous. Those same thousands of volts, but with real flow behind them, would be deadly. Static electricity is all pressure and no flow, a braggart that startles you but does almost no harm. These charges, moreover, do not come in just any amount. They come in exact packets, in multiples of one minimum, indivisible unit, the charge of a single electron. There is no half a charge of an electron, no loose third floating about. Charge always comes in whole grains, like grains of sand, and the smallest grain is the one an electron carries. This was proven beautifully by an American physicist named Robert Millikan at the beginning of the 20th century, with an experiment so elegant it has become famous. Millikan sprayed microscopic droplets of oil into a chamber and let them fall between two electrically charged plates. By adjusting the electricity on the plates, he managed to stop a droplet in the air, to leave it floating still, balancing exactly the electric force pushing it up against the weight pulling it down. And by measuring that force precisely, he could calculate the charge on each droplet, and he found that all the charges he measured were always exact multiples of the same tiny number, never loose fractions. That number, that minimum grain of electricity, was the charge of a single electron, one of the smallest and most fundamental figures in all of physics. Millikan had weighed, so to speak, the smallest coin in the electric universe. With this, we already have the basic piece. Electricity is, at bottom, a matter of electrons, those very light particles with a negative charge that flit about in atoms and that, in certain materials, can come loose and move. And here comes the next great question, the one that leads us to the heart of what electricity is for. Because one thing is charge sitting still, gathered, static, the charge of amber and the balloon and the shock from the door handle. And another, quite different thing is charge in motion, flowing, the electric current, which is the one that truly makes the world work. What exactly is an electric current? What moves? And how do you turn on a light? The answer holds one of the most delightful surprises in all of this story. An electric current is simply charge in motion. In the metal wires of your house, that charge is electrons. Metals have a special property that makes them perfect for conducting electricity. In a metal, some of the electrons of each atom are not firmly tied to their nucleus, but are loose, free, forming a kind of sea of electrons that can move throughout the whole material. Imagine the metal as a rigid grid of fixed atoms, and among them an ocean of free electrons that can drift about. When you connect that metal to a pile or a plug, you push that ocean of electrons to move, all in a certain direction, and that collective movement of electrons is the electric current. The materials that have those free electrons, like metals, conduct electricity well, and we call them conductors. The materials that do not, whose electrons are firmly held, do not let current pass, and we call them insulators, like plastic, glass, rubber, dry wood. That is why cables are metal on the inside, to conduct, and wrapped in plastic on the outside to insulate, so they do not shock you when you touch them. And now comes the surprise, one of the most counterintuitive and beautiful things in all of electricity, and one that almost no one knows. When you flip a switch, the light comes on instantly, does it not? You press the button, and in that very instant, with no noticeable delay, the bulb lights up, even if it is many meters away from the switch. This makes us think the electrons must travel down the wire at a dizzying speed, that they shoot out of the switch and reach the bulb like bullets. Well, it is exactly the opposite. The electrons inside a wire move terribly slowly, unbelievably slowly. In a normal cable in your house, with the current flowing, each individual electron advances along the wire at a speed of less than 1 millimeter per second. Slower than a snail, slower than the hour hand of a clock. If you could mark one particular electron and follow it, it would take more than an hour to travel a single meter of cable. So how can it be that the light comes on instantly, if the electrons are so slow? The answer lies in a beautiful analogy. Imagine a very long pipe, completely full of water, or better still, full of marbles, one behind another, touching with no gap at all, from one end to the other. Now you push one new marble in at one end of the pipe. Instantly, with almost no delay, a marble comes out the other side. It is not the marble you pushed that one has barely moved. What has happened is that your push has been transmitted from marble to marble along the whole pipe, almost at the speed of light, and has made one come out at the far end. The push travels lightning fast. The marbles, each of them, barely move. Well, in the wire, exactly that happens. The wire is already full of electrons from end to end, like the pipe full of marbles. When you press the switch, you do not have to wait for an electron to travel from the switch to the bulb. You simply push all the electrons at once, and that push, that signal, that electric field, propagates down the wire at nearly the speed of light, setting in motion. Instantly, the electrons that were already sitting right next to the bulb lights up immediately because the electrons that light it were already there, waiting for the push. Each electron moves terribly slowly, but the push travels lightning fast. And that, exactly that, was the paradox hidden in the jump of Nolit's monks. The monks all leapt at once, in the same instant, because the signal traveled down the chain almost instantly, even though no electron actually traveled the whole mile of the circle. This analogy of the full pipe, the water or the marbles, is one of the best there is for understanding electricity, and we will use it more tonight. But like every analogy, it has its limits, and it is worth knowing them so we do not fool ourselves. The main one is that water can come out the open end of a pipe and fall on the floor, whereas electricity does not work that way. Electricity always needs a closed circuit, a complete round trip, a loop. The electrons do not get used up or vanish out the end of the wire. They go all the way around and come back. That is why every electrical device has two connections, two wires or two poles, one for the way there and one for the way back. The current leaves the pile or the plug, runs through the device making it work, and returns by the other wire. If the circuit breaks at any point, if you cut the loop, the current stops completely, instantly, everywhere. The way water stops in a ring of pipes if you close a valve. That is why a switch, which is nothing more than a bridge that opens and closes in the circuit, turns off the light instantly. It is not that it empties the wire of electricity, it is that it breaks the loop, and without a closed loop, no current is possible. There are two ways of making electrons move down a wire, and they give rise to the two great kinds of electric current whose names you have surely heard. There is direct current, in which the electrons flow always in the same direction, steadily, like a river that always runs the same way. It is the kind produced by piles and batteries. The negative pole pushes the electrons, which run around the circuit in a single direction to the positive pole. Volta's pile gave direct current, and the battery in your phone does too. And there is alternating current, which is stranger and more ingenious, and it is the one that arrives at the plugs in your house. In alternating current, the electrons do not advance in a fixed direction, but change direction very many times per second, forward and back, vibrating in place. In Europe, the current in the plugs changes direction 100 times per second. In America, 120. The electrons barely move at all. They only vibrate to one side and the other, without really advancing as a group, a lightning-quick shudder of microns. And yet that shudder carries the energy just as well, because what carries the energy is not the journey of the electrons, but the push that propagates among them. It may seem an absurd system. Why make the electrons vibrate instead of advance? But it turns out alternating current has a gigantic practical advantage for carrying energy over long distances, an advantage that was the key to one of the fiercest commercial wars in history, the one that set Edison against Tesla, and which we will tell later. Think of it with an image. Imagine a carpenter's saw cutting through a log. The blade of the saw barely moves. It comes and goes back and forth without advancing as a whole, and yet it transmits a great deal of energy to the wood and cuts it. The teeth of the saw vibrate in place like the electrons of alternating current, and still they do the work. The energy does not travel because the blade moves from one place to another, but because the back and forth is transmitted with force. With alternating electricity, something similar happens. The electrons barely move from their place. They come and go 100 times a second, but that coordinated trembling carries enormous amounts of energy along the wires. For now, hold on to the image of those electrons vibrating 100 times a second in the wires of your wall, still in their place, but trembling without rest, carrying to your lamp the energy of a power station that may be hundreds of kilometers away. We already know what current is. We are missing two concepts to complete the basic picture of electricity. Two words you have surely heard 1,000 times without being quite sure what they mean: voltage and resistance. And with a good analogy, you are going to understand them forever. Let us go back to the water pipe, because it is the best way to understand this. Imagine a water tank raised high on top of a tower, connected by a pipe to a tap below. The water flows down the pipe, pushed by the height, by the difference between the tank above and the tap below. The higher the tank, the more pressure the water has, the more forcefully it comes out. That pressure, that push that makes the water move, is the equivalent of voltage in electricity. Voltage is the electrical pressure, the push that makes the electrons move. Technically, it is called a potential difference, and that word, difference, is the key. Voltage is always a difference between 2 points. Just like the pressure of water depends on the difference in height between the tank and the tap, a 1.5 volt battery has that much difference in push between its 2 poles. A plug in your house, in Europe, has 230 volts of difference between its 2 holes, and a bolt of lightning, to give you a sense of the scale, has a difference of more than 100 million volts between the cloud and the ground. Voltage is the force, the pressure, the will that electricity has to move. Current, on the other hand, following the pipe analogy, is the amount of water that passes, the flow. How much water flows per second? In electricity, it is how many electrons pass per second through a point in the wire, and it is measured in amperes. Voltage and current are different things, and it is worth not confusing them. Voltage is the pressure, the will to move. Current is the actual flow, how much actually moves. You can have a lot of voltage and little current, like a very high tank connected to a very thin pipe through which barely a trickle drips out despite the enormous pressure. Or a little voltage and a lot of current, like a low tank connected to a very wide pipe through which a great deal of water passes with hardly any pressure. This distinction, by the way, explains why sometimes a discharge of high voltage but very little current, like the shock from the door handle, with its thousands of volts, only gives you a fright, while other discharges of less voltage but a lot of current can be deadly. What truly does harm is not so much the pressure as the flow, the amount of electricity that crosses through the body. And the third piece is missing: resistance, back to the pipe. If the pipe is wide and smooth, the water passes easily. If it is narrow or full of bends and obstacles, the water has a harder time getting through. It meets opposition. That opposition to passage is resistance. In electricity, resistance is what opposes the flow of the electrons, what makes it difficult for them to move. Some materials have little resistance and let the current pass easily, like the good conductors, copper and silver. Others have a lot of resistance, and here something very useful happens, because when the electrons have to force their way through a material with resistance, heat is generated. That is the principle of a great many everyday devices. The filament of an old bulb has so much resistance that as the current passes, it heats up until it glows white hot and gives off light. The resistance of an electric stove, a toaster, a hair dryer, an iron, heats up as the current passes and produces the heat we are looking for. Every time a device generates heat from electricity, it is taking advantage of resistance, the friction of the electrons as they force their way through. These 3 quantities, voltage, current, and resistance, are joined by a relationship so simple and so important that it is the first formula any student of electricity learns, and it is called Ohm's law after the German physicist Georg Ohm. The law says, in plain words, that the current that flows is equal to the voltage divided by the resistance. Or, put another way, the more voltage, more pressure, the more current flows, and the more resistance, more opposition, the less current passes. It is pure common sense if you think of the pipe. More pressure, more water. A narrower pipe, less water. The unit of resistance, the ohm, carries Ohm's name, just as the volt carries voltas and the ampere carries the name of a French physicist, Ampère, who studied currents. The great names of electricity have stayed with us forever, turned into the units with which we measure it. Every time you speak of volts, amperes, and ohms, you are invoking three scientists from 2 centuries ago. It is worth saying, to be honest, that Ohm's law is a beautiful simplification that works very well in many cases, but not all. There are materials and devices that do not obey it cleanly, in which the relationship between voltage and current is more complicated. The filament of the bulb itself changes its resistance as it heats. But as a first approximation, as a way of understanding how the three basic quantities of electricity relate, Ohm's law is a marvel of simplicity and usefulness, and there is a fourth quantity that gathers them all together, and that is, at bottom, what you actually pay for on your electricity bill. Power, electrical power, is the speed with which energy is consumed or transferred, and it results from multiplying voltage by current. It is measured in watts, in honor of James Watt, the man of the steam engine. A low-consumption bulb may be a few watts, a hairdryer a couple of thousand. When the electric company charges you, it does not charge you for volts or for amperes, but for the total energy you have used over time, those kilowatt hours that appear on the bill. 1 kilowatt hour is the energy a 1,000-watt device uses running for 1 hour. The whole accounting of your bill, the whole worldwide electricity business, comes down, at bottom, to measuring how much electrical energy you have used. How many of those electrons, pushed through your devices, have given up their energy to give you light, heat, movement, or information. With this, you already have the basic conceptual kit: charge, current, voltage, resistance, power, the bricks with which all of electricity is built. And now that you understand these pieces, you can truly understand something very practical, and that many people have learned wrong. Why and how electricity can kill, and why sometimes it does nothing at all. What is dangerous to the human body is not directly the voltage, the pressure, but the current, the flow of electrons that manages to cross through the body. And since current depends on voltage divided by resistance, everything comes down to the resistance your body offers to the passage of the electricity. Dry skin has a fairly high resistance, offers a decent barrier, and that is why many light contacts only give a fright. But wet or sweaty skin lowers that resistance enormously, and then the same voltage can push through a much larger, much more dangerous current. That is why electricity and water are such a feared combination, and why you should never touch electrical devices with wet hands, or in the bathtub. It is not that water has anything magical about it. It is that it lowers the resistance of your skin and opens the door for more current to enter. It takes a surprisingly small current crossing the chest to disturb the electrical rhythm of the heart, that natural pacemaker we will talk about, and to make it fall into fibrillation and stop pumping. That is, in most cases, the mechanism by which a shock kills. It does not burn or destroy, it simply disorders the delicate electricity of the heart. And that is also why that shock from the door handle, with its thousands of volts but its ridiculous amount of charge, does nothing to you but startle you. A lot of pressure, very little flow, and along a path that does not cross the heart. Electricity, like almost everything in nature, is neither good nor bad. It is a force, and everything depends on the amount, the path, and the circumstances. The same force that lights your lamp could stop your heart, And the same one that could stop your heart, well dosed, is what a defibrillator uses to start it again. But there remains the deepest connection of all to understand, the one Arsted glimpsed with his compass and Faraday turned into a dynamo. The one that explains where the electricity in your house truly comes from. The secret connection between electricity and magnetism. And to understand it completely, we have to go back to that quiet young Scotsman I promised to introduce. The man who discovered that light is traveling electricity. His name was James Clerk Maxwell. He had been born in Scotland in 1831, the same year Faraday discovered induction, and he was one of those rare geniuses who appear only a few times per century. As a child, he was so curious that he drove his family half mad by asking about everything. How does this work? What is that made of? What makes the thing over there move? He published his first scientific paper at 14, and as an adult, he became a physicist of astonishing mathematical power. But also, and this is rare in a genius of his stature, a modest man, kind, deeply religious, without a drop of the arrogance that usually accompanies great intelligences. Maxwell admired Faraday enormously, and although they could not have been more different, the self-taught bookbinder without mathematics, and the Scottish mathematician of exquisite training, between the two of them, adding their opposite talents together, they built one of the peaks of human thought. What Maxwell did was to take all of Faraday's intuitions, those lines of force, those fields that filled space, and translate them into the rigorous and precise language of mathematics. Faraday had seen the images. Maxwell wrote the equations. And in doing so, in putting into formulas everything that was known about electricity and magnetism, Maxwell managed to unite the two forces into a single theory, into a handful of elegant equations that described, at once and in a unified way, all electrical phenomena and all magnetic phenomena. They were no longer two things, electricity and magnetism. They were two faces of a single force that, from then on, would be called electromagnetism. That alone would have been enough to go down in history. But Maxwell found within his own equations a surprise that left even him astonished. And that is one of the most beautiful revelations in all of science. His equations said something extraordinary. They said that an electric field that changes creates a magnetic field, and that a magnetic field that changes creates an electric field. Notice the circle that forms. If, somewhere, an electric field changes, that change generates a magnetic field around it. And if that magnetic field also changes, it generates, in turn, an electric field, which generates another magnetic one. Maxwell realized this meant that the fields could sustain one another, feed one another, and so travel through space in a perpetual dance of electric field and magnetic field, creating each other in turn and propagating forward. A wave, an electromagnetic wave made of pure field, of pure electric and magnetic influence intertwined, able to travel through the vacuum with no need of any wire or any medium. And then Maxwell calculated, from his equations, at what speed that electromagnetic wave would travel. He did the arithmetic, and a number came out, a very specific speed, and when he looked at that number, his blood must have run cold with wonder, because he recognized it. It was the speed of light. The speed at which his theoretical electromagnetic wave traveled coincided, with astonishing precision, with the speed of light that astronomers and physicists had measured by other methods. And it could not be a coincidence. There was only one possible explanation. And Maxwell wrote it down with the contained emotion of someone who has just understood a secret of the universe. Light itself is an electromagnetic wave. Light is electricity and magnetism traveling together through space. The light that comes from the sun, the one that lets you see, the one that lights this room, is exactly the same phenomenon as the electricity of the wires and the magnetism of the magnets, only oscillating at a very high frequency and propagating through the vacuum. In a single stroke, with a handful of equations, Maxwell had united three of the great mysteries of nature that seemed to have nothing to do with one another: electricity, magnetism, and light. They were the same thing, three faces of a single reality. The consequences of this are hard to overstate, and they fill your entire life, though you never notice. Because if light is an electromagnetic wave oscillating at a certain frequency, what happens with electromagnetic waves that oscillate at other frequencies, slower or faster? Maxwell predicted that they must exist, even though our eyes could not see them. And they exist, all of them exist. They form what we call the electromagnetic spectrum, an immense family of waves that are all, absolutely all, the same thing as light, only vibrating at different frequencies. The ones that vibrate more slowly than visible light are radio waves, microwaves, infrared. The ones that vibrate faster are ultraviolet light, X-rays, gamma rays, and in the middle, in a very narrow band, is the only part our eyes can see, visible light, with its colors from red to violet. But it is only a tiny slit in an immense reality. We live surrounded, crossed at every moment by an ocean of invisible electromagnetic waves. And here is the revelation that connects Maxwell with your daily life. The radio waves you listen to music with in the car are electromagnetic waves, invisible light. The signal of your television, invisible light. The microwaves that heat your food, invisible light of a specific frequency that makes the water molecules vibrate. The remote control works with infrared, invisible light. And above all, the Wi-Fi in your house, the signal of your mobile phone, the Bluetooth of your headphones. All of that is electromagnetic waves. All of that is, literally, light your eyes cannot see, generated and captured by antennas, traveling through the air at the speed of light, because it is light. When your phone connects to the Wi-Fi, it is bathed in an invisible light that carries the information. The whole civilization of telecommunications, radio, television, mobile phones, wireless internet, satellites, GPS, all of it is a direct child of that moment when a modest Scotsman did the arithmetic and discovered, trembling, that light and electricity are the same thing. We live, without knowing it, inside Maxwell's discovery, wrapped at every second in the invisible light he predicted. Maxwell did not live to see his prediction of invisible waves confirmed by experiment. He died young of an abdominal cancer at 48, the same illness that had killed his mother when he was a child. It was only a few years after his death that a German physicist, Heinrich Hertz, managed to generate and detect radio waves in the laboratory, proving that Maxwell was entirely right. When Hertz was asked what those invisible waves he had discovered were good for, he answered that they were good for nothing, that they had no practical use, that they only served to prove that the master Maxwell was right. He could not imagine that on those useless waves would be built in a few decades the whole world of telecommunications. Once again, Faraday's newborn baby, the apparently useless science that ends up transforming the world. And in honor of Hertz, by the way, we measure frequencies today in hertz. When you read that your Wi-Fi runs at so many gigahertz, you are naming the man who first captured Maxwell's invisible light. It is worth saying, because it tends to be forgotten, that Maxwell was not only the man of electromagnetism. His prodigious mind touched almost everything it brushed against. He explained what the rings of Saturn are made of, showing with pure mathematics that they could not be solid or liquid, but had to be formed of countless independent particles, something the space probes would confirm a century later. He laid the foundations of the theory that explains the behavior of gases from the movement of their molecules. And he produced, in 1861, the first permanent color photograph in history, the image of a Scottish tartan ribbon, showing that any color can be obtained by combining red, green, and blue light. Exactly the principle by which every screen in the world works today, including the one on which you may be listening to this. A single man, modest and gentle, dead before turning 50, left his mark on electromagnetism, on astronomy, on the physics of gases, and on color photography. And yet, outside the circles of science, almost no one knows his name. It is one of those quiet injustices of history that Faraday and Maxwell, two of the greatest benefactors of humanity, should be as little celebrated as they are. While the whole world they built hums and shines around us at every second, with Maxwell, the deep understanding of electricity was, in essence, complete. We knew what it was, how it moved, and that it was the sister of light. What was missing was the most practical and the most transformative part, to bring all that understanding to the streets, to the houses, to the lives of ordinary people. What was missing was to electrify the world, and that feat, to turn the science of electricity into the civilization of electricity, set off a war. A fierce, dirty war, full of genius and cruelty, between two of the most fascinating characters in history, Thomas Edison and Nikola Tesla. To understand the war, first you have to understand the two contenders, because they could not have been more different. In one corner, Thomas Alva Edison, the American par excellence, the inventor turned businessman, the practical man. Edison was not so much a theoretical scientist as a genius of applied invention and of teamwork. He set up, in Menlo Park, in New Jersey, something that had not existed before, a factory for inventing, an industrial laboratory with dozens of assistants working in parallel, testing thousands of combinations until they hit on what worked. His motto was that genius is 1% inspiration and 99% perspiration, sweat, and with that method of brute force and persistence. He brought forth a great many inventions that changed the world: the phonograph, for recording sound, improvements to the telegraph and the telephone, and above all, the invention with which his name was joined forever, the electric light bulb. Here it is worth another pause to add nuance, because about Edison and the bulb, too, there is a legend that simplifies too much. It is not entirely true that Edison invented the bulb out of nothing. The idea of producing light by heating a filament with electricity was older than he was, and several inventors in different countries, above all an Englishman named Joseph Swan, had made bulbs before or at the same time as Edison. What Edison achieved, and it is no small thing, was to create the first truly practical and commercial bulb, with a filament that lasted a long time, a good vacuum inside the glass. And above all, and this is the brilliant part, Edison did not just invent the bulb, he invented the whole system that made it useful. A bulb is no use if you have no electricity in the house to light it, so Edison designed the power stations, the cables, the meters, the switches, the whole system of generation and distribution that carried electricity from a station to every bulb in every house. He built the first commercial electric grid in history in New York and began to light the city. Edison did not sell bulbs, he sold light as a service delivered to your home. And that vision of a complete system was his true stroke of genius. But Edison's system had an Achilles heel, and that is where the other protagonist comes in. Edison's electricity was direct current, the kind in which electrons flow always in the same direction. And direct current has a serious problem for distributing it. It loses a great deal of energy when it travels over long distances through the cables, so much that Edison's stations could only serve a radius of a few blocks. To electrify a whole city, you would have to fill it with stations everywhere, which was hugely expensive and unworkable. A way had to be found to carry electricity far, over great distances, without losing it along the way. And the solution had to do with alternating current, the other kind, in which the electrons vibrate instead of advancing. Alternating current has a magical property. Its voltage can be raised and lowered easily using a device called a transformer. And it turns out that if you carry electricity at very high voltage, very little energy is lost along the way, even if it travels hundreds of kilometers. Then, on reaching the houses, the voltage is lowered to a safe level. Alternating current made it possible to bring electricity far, from great stations to whole cities. It was technically far superior for distribution. And the great champion of alternating current was a Serbian immigrant, a strange and visionary genius who had worked briefly for Edison before turning against him, Nikola Tesla. Tesla is one of the most fascinating figures in the whole history of science, a genuine genius wrapped in eccentricity and tragedy. He had been born in what is today Croatia, the son of a Serbian Orthodox priest, and he had a prodigious and very strange mind. He said that ideas appeared to him as complete visions, that he could build and test whole machines in his imagination without needing to draw them. He emigrated to America with almost nothing in his pocket and a letter of recommendation. He worked for a time for Edison, they quarreled, and he ended up allying himself with a competitor of Edison's, the industrialist George Westinghouse, who bought Tesla's patents on the alternating current motor and bet on that system, and so broke out what became known as the War of the Currents. Edison with his direct current, Tesla and Westinghouse with alternating, fighting for the electric standard that would rule the world. It was not just a technical dispute. There were immense fortunes at stake, the control of the electrification of an entire country and, behind it, the whole planet. And Edison, who was a fierce businessman as much as an inventor, waged that war with methods that seem repugnant to us today. Knowing that his direct current was technically inferior for distribution, Edison decided to attack alternating current from another flank, that of fear. He launched a campaign to convince the public that alternating current with its high voltage was mortally dangerous, much more so than his own. And to prove it, he sponsored a series of macabre demonstrations. Collaborators of his publicly electrocuted animals with alternating current, dogs, cats, horses, to show how lethal it was. They even coined a sinister verb, to be Westinghoused, as a synonym for dying electrocuted, to associate the rival's name with death. And the campaign reached a grim extreme when alternating current was used to create a new method of execution, the electric chair. The first execution in the electric chair, that of a murderer named William Kemmler in 1890, was a ghastly and botched spectacle. The first discharge did not kill him, and a second had to be applied, long and horrible, until the flesh began to burn in front of the witnesses. Westinghouse himself, horrified, remarked that they would have done better with an axe. Behind that execution there was, in fact, a deliberate maneuver. Edison's partisans had pushed, in secret, for the electric chair to use alternating current, the rivals, precisely to associate in the public mind Tesla's system with death. Westinghouse, aware of the ploy, went so far as to finance Kemmler's legal defense, not out of compassion for the condemned man, but to keep his current from being tied forever to capital punishment. He lost the case, and the alternating current electric chair became a method of execution that would endure for almost a century in some places. It is one of the most sinister episodes in all the history of technology. Two companies fighting over the electricity market, using the body of a condemned man as a battlefield for advertising. Here it is worth taking apart another much-repeated myth, that of the elephant Topsy. It is often said that Edison electrocuted an elephant named Topsy to discredit alternating current, and a film of the event is even preserved, with Edison's name in the credits. The reality is more nuanced. Topsy, an elephant at an amusement park on Coney Island, was indeed electrocuted in 1903, after having killed a man who mistreated her. But by then the War of the Currents had been over for years, and Edison was not present and did not make the decision. The confusion comes from the fact that the film was distributed by a company that bore his commercial name. The decision to kill poor Topsy was made by the owners of the park, for reasons that had nothing to do with the electrical dispute. It is a good example of how legends stick to famous figures and end up being told as truths. Edison did quite ugly things in the War of the Currents. There is no need to attribute to him, on top of that, one he did not commit. And who won the war? Alternating current won it. Tesla won it, or rather his system did. Because when the time came to undertake the greatest electrical project of the era, to harness the colossal force of Niagara Falls to generate electricity and carry it to the city of Buffalo, more than 30 kilometers away. Edison's direct current stood no chance. Only alternating current could carry the energy so far. Niagara had been the dream of engineers for generations. A practically infinite amount of energy falling day and night, millions of liters of water plunging without rest, a force that humanity had spent centuries contemplating with reverence and never being able to use for more than to turn some nearby mill. To tame Niagara, to turn that roar of water into electricity and send it to the cities, was the definitive test, the final exam of the new electric age. And there was a fierce debate over which system to use, with the best engineers in the world divided. In the end, the contract went to Tesla and Westinghouse, and in 1895, the Niagara Station began to send alternating current electricity to Buffalo, demonstrating to the whole world the superiority of the system. It is said that when the energy of Niagara reached the city for the first time, there were celebrations, because it was the tangible proof that the brute force of nature could be captured and handed out, gentle and useful, to homes and factories kilometers away. From then on, alternating current prevailed across the whole planet, and that is why, today, the electricity that reaches the plugs in your house, in any country in the world, is alternating current, Tesla's, the one that makes the electrons vibrate 100 times a second. Every time you plug something in, you are using the system that Tesla and Edison went to war over more than a century ago. The Serbian immigrant of the visions won. Although, as we will see, winning the technical war did not make him happy, because the story of Nikola Tesla, after winning the War of the Currents, is one of the saddest and strangest that science has ever produced. Tesla was a genius, but also a man tormented by obsessions and oddities that we might today recognize, perhaps, as a disorder. He was obsessed with the number 3, and had to do many things in groups of 3 or multiples of 3. He was terrified of pearls to the point of refusing to speak with a woman who wore them. He was obsessively clean, terrified of germs, and demanded in restaurants an exact number of napkins, and calculated in his head the volume of every dish before eating. He counted his steps as he walked. He lived alone in hotels, given over entirely to his ideas, with almost no close human relationships. And his ideas grew ever grander, ever more visionary, and also ever harder to sell. Tesla dreamed of things that sounded like science fiction and that, in many cases, ran decades ahead of his time. In his laboratory in Colorado Springs, he produced giant artificial lightning bolts, discharges of millions of volts that made a roar heard for kilometers, and he claimed to have lit bulbs at a distance, without wires. The tool with which he produced those bolts, the Tesla coil, is still today one of the stars of science museums and electric shows, able to throw serpents of electricity meters long amid thunderous cracklings. Tesla put on genuine performances with it, letting the current apparently pass through himself while he held bulbs that lit up on their own in his hands, wrapped in a halo of sparks, half scientist, half stage magician. He loved to astonish, and he knew that astonishment drew in the investors he needed for his ever grander dreams. And his most ambitious dream, the one that consumed him, was to transmit electrical energy wirelessly through the earth itself, to give free electricity to all of humanity, in any corner of the planet, with no wires, no meters, no charge. To achieve it, he began to build on Long Island an immense tower, the Wardenclyffe Tower, with an enormous dome. Financed at first by one of the richest men in the world, the banker J.P. Morgan. But when Morgan understood that Tesla's final goal was, no more and no less, free energy for everyone, it is said he asked where the business was in that, where you would put the meter to charge, and withdrew the funding. Without money, the tower was left half-built, fell into ruin, and was finally demolished and sold for scrap. Tesla's great dream, free electricity for all humanity, collapsed into the dust. Tesla's final years were of a moving sadness. The man whose system lit the whole world lived ever poorer and more isolated, in hotel rooms while his debts piled up, and he found comfort in an unexpected place. In pigeons. Tesla, who could barely bear human contact, developed a deep and tender love for the pigeons of New York. He fed them in the parks, took the injured ones up to his room to heal them, spent money he did not have caring for them, and came to speak of one white pigeon in particular. A female he said he had loved as one loves a person. He told how that pigeon would come to visit him, that there was a special understanding between them, and that the day the pigeon died, he felt that something went out inside him too, that the purpose of his work and his life left with her. It is a heartbreaking image. One of the greatest geniuses in history, the man who electrified the planet, alone in a hotel room, speaking of love to a white pigeon. Tesla died poor and alone in January of 1943 in room 3327 of the Hotel New Yorker. The rent of that room, in a final gesture of irony and perhaps of guilt, had been paid for some time by the Westinghouse Company, the same one with which, decades earlier, he had won the War of the Currents. Months after his death, the Supreme Court of his country recognized that Tesla, and not Marconi, had been the true pioneer of radio, a posthumous recognition like so many that come too late. It is worth, to be fair, adding nuance to the legend of Tesla too, because in recent times he has become a kind of holy martyr of science, the good genius crushed by the wicked Edison. And the reality is more nuanced, as always. Tesla did not invent alternating current, which existed before him. His brilliant contribution was the alternating current motor and the system for using it practically. And Edison, with all that was ugly in his behavior during the War of the Currents, was an extraordinary inventor and organizer who made immense contributions. There is no hero and no villain. There are two brilliant and deeply imperfect men who, between the two of them, with their struggles and their meanness, electrified the world. Real history almost never has clean good guys and bad guys. It has complicated human beings doing great and small things at the same time. And the result of all of that, of Volta and Faraday and Maxwell and Edison and Tesla and so many others, was one of the deepest and fastest transformations in all the history of humanity. Think about what it meant. For all of earlier history, for tens of thousands of years, human life had been governed by the sun. People worked by day and slept by night, because the night was darkness, barely broken by the trembling flame of a candle, an oil lamp, a fire. Darkness set the rhythm of life, imposed its limits. And suddenly, in barely a few decades, straddling the 19th and 20th centuries, the electric light arrived, and the night broke open. The cities lit up, the streets, the houses, the factories filled with a clean, constant, smokeless light that came on at the touch of a finger. The first theater in the world, lit entirely by bulbs, in London, left the audience astonished. Factories could work at night. People could read, sew, live after sunset, without ruining their eyes with candles. The human day grew longer. The ancient fear of the dark began to dissolve. And it was not only the light. With electricity came the motors that moved machines without any need of steam or animal strength, the trams and electric trains, the telegraph and then the telephone that annihilated distances, the radio that carried voices through the air. Each decade, electricity worked itself deeper into everyday life, until it became as omnipresent and invisible as the air. Think for a moment about what each of these things meant to the person who lived through it for the first time. The first time someone, used to the trembling gloom of candles, walked into a room and, by merely turning a key, flooded it with a firm white light. No smoke, no smell, no danger of fire, must have felt something close to magic. The first time a human voice came out of a box on the other end of a wire, speaking from another city, people crossed themselves or drew back in fright. The first time Music sounded in a house with no musicians present, coming from a radio set. Families gathered around the device the way they used to gather around the fire. Each of these marvels, which to us are dull routine, was in its moment an astonishment that bordered on the religious. And all of them, absolutely all of them, were children of electricity, of those games with amber and frogs and bottles that for centuries seemed to be good for nothing. In barely 2 or 3 generations, humanity passed from a world lit by fire, essentially the same sensory world as the ancient Romans or the people of the caves, to a world of electric light, voices at a distance, and music in the air. Few transformations so radical has our species ever lived through, and it happened so fast that the people who were born by candlelight died listening to the radio and watching airplanes cross the lit-up sky. Today, when there is a blackout and the light goes out all at once, we feel an almost primitive helplessness, and we discover suddenly how many things in our lives secretly depend on that constant flow of electrons we take for granted. The fridge, the heating, the hot water, the internet, the phone, the traffic light, the hospital, everything stops. In barely a century and a half, humanity passed from living by candlelight to building an entire civilization hung from electricity, so dependent on it that a prolonged cut would paralyze it completely. It is a transformation so enormous and so recent that we have not yet fully taken it in. We live, without knowing it, inside the work of those men who chased sparks. But we have spoken a great deal about the electricity of wires, the electricity of machines and cities, and there is another electricity, far older, far more intimate, that you carry inside you right now, and that is, if anything, even more astonishing. The electricity of life, the one Galvani was right to sense all those years ago with his frog legs, because you, in this very instant, while you listen to these words and perhaps begin to feel your eyelids grow heavy, are an electric creature. Your heart beats by electricity. Your thoughts are electricity. Every movement, every sensation, every memory is a tiny bolt of lightning running across the geography of your body. Let us lean in, gently, over that silent storm that is you. Galvani, remember, believed he had discovered an animal electricity, a vital electric force in living tissue. Volta proved to him that the current in his experiments came from the metals, not from the frog, and he won the dispute. But it turns out that, at the very deepest level, Galvani was right in a way that not even he could fully prove, because living beings do run on electricity. Not the same electricity as the wires, not electrons flowing through metals, but a version of our own, chemical, subtler, and in a way more marvelous, but electricity, in the end. Your body is right now a marvel of electrical engineering that no human machine has yet equaled in elegance. Let us start with the nerves, with how your brain sends orders to your muscles and how it receives information from your senses. All of that travels down the nerves in the form of electrical signals. Each neuron, each nerve cell, is like a tiny living cable that transmits electrical impulses. But the mechanism is different and fascinating. A neuron at rest maintains a difference in electric charge between its interior and its exterior, a small living battery. The inside of the cell is charged negatively with respect to the outside, with a difference of about 70,000ths of a volt. It is a minuscule voltage compared to a plug, but at the scale of a cell it is enormous, and enough. And how does the cell maintain that difference? With tiny molecular machines embedded in its membrane, pumps that work without rest, expelling some ions and letting others in, sodium out, potassium in, keeping the charge imbalance going, like someone bailing water out of a boat without stopping. Those pumps are working in every one of your neurons right now, millions upon millions of them, consuming a significant part of all the energy you spend, just to keep your cells charged and ready to fire. And when the neuron activates, when it transmits a signal, something lovely happens. At one point on the cell, some gates suddenly open, and the charged ions rush in, momentarily reversing the charge at that point, which goes from negative to positive in an instant. And that change of charge opens the gates next to it, which reverse too, and the ones beyond that, in a chain reaction that runs down the neuron from end to end, like a wave, like a flame running along a fuse. That is the nerve impulse, the action potential, the basic unit of thought and of sensation, a wave of electrical change traveling down the cell. And it travels fast. In the fastest nerve fibers, it reaches more than 100 meters per second, more than 400 kilometers an hour. And how does the body achieve that speed? With a lovely engineering trick. The fastest nerves are covered in an insulating sheath made of a fatty substance called myelin, which wraps the nerve the way plastic wraps a cable, but leaving small gaps at regular intervals. And the electric impulse, instead of running down the whole fiber centimeter by centimeter, jumps from gap to gap, leaping over the insulated stretches, which multiplies its speed enormously. It is as though, instead of walking the whole way, you took great leaps from lamppost to lamppost. When that myelin sheath is damaged, in certain illnesses the impulses slow down or get lost, and the body stops obeying or stops feeling well, which shows how deeply your everyday life depends on those microscopic insulators wrapping your nerves. When you prick a finger, the signal of pain runs down your nerves to the brain at the speed of a bullet train. When you decide to move your hand, the order comes down from your brain to the muscles at that same dizzying speed. Thousands of millions of these tiny bolts run through your nervous system in every second of your life, weaving together everything you feel, think, remember, and do. In this very moment, while you understand these words, armies of electrical impulses are crossing your brain, switching on and off in patterns of a complexity that dwarfs any computer. To hear this sentence is, physically, an orderly electric storm inside your head. And then there is your heart, which is perhaps the most beautiful example of all, because it is a pump moved by electricity that never, in your whole life, stops. Your heart is beating now, as you listen to this, and it has been beating without rest since before you were born. And it beats thanks to an electric spark that it generates by itself. In one corner of the heart there is a small group of very special cells, the sinus node, which is the natural pacemaker of the heart. Those cells generate, all on their own, a rhythmic electrical impulse, a spark that fires some 60 or 70 times a minute at rest without anyone ordering it automatically. And each of those sparks propagates through the muscle of the heart, coordinating the contraction of its chambers in precise order. First the upper ones, then the lower, so the heart pumps the blood efficiently. Beat, beat, one electric spark after another, thousands of millions of times across a lifetime, without rest, without failing, in the darkness of your chest. That electrical activity of the heart is what an electrocardiogram records, that drawing of peaks and valleys you have seen in films and in hospitals, with its rhythmic beep. Each peak of that drawing is one of those sparks running through your heart. The device that captures those signals was perfected more than a century ago by a Dutch doctor named Willem Einthoven, who built a galvanometer so sensitive it could detect the minuscule currents of the heart through the skin, and who named the different waves of the heartbeat with letters that cardiologists still use today, all over the world. For that invention he received the Nobel Prize, and thanks to him, every time a doctor looks at the tracing of your heart, they are reading an electrical language invented by a patient Dutchman more than 100 years ago. And when the electrical rhythm of the heart falls out of order, when it collapses into the chaos we call fibrillation and stops pumping, the way to save the person is precisely to apply a powerful electric discharge with a defibrillator, the one that in films makes the body jump, to reset all at once the electrical system of the heart and give it back its rhythm. It switches off and switches on again, like a computer that is frozen. Life and death, sometimes, depending on a spark well given. And there is a lovely historical irony in this, because what Aldini clumsily sensed with his shuddering corpses, the idea that an electric discharge might return movement to a stopped body, has become, 2 centuries later, a technology that truly saves lives every day in every hospital in the world. The macabre galvanism of the fares turned, with time and knowledge, into the defibrillator that restarts hearts. Even your entire brain, the most complex organ in the known universe, runs on electricity, and its combined electrical activity can be measured. If they place electrodes on your scalp, a device called an electroencephalograph can pick up the electrical murmur of your thousands of millions of neurons working at once, faint rhythmic brain waves of barely millionths of a volt that change according to whether you are awake, focused, relaxed, or asleep. The first to capture those waves was a German psychiatrist, Hans Berger, a reserved and somewhat tormented man who for years pursued the idea in secret, half convinced that the brain gave off a kind of energy that could explain telepathy. He found no telepathy at all, but he found something almost as astonishing: the electrical rhythm of the human brain, the waves that today bear his name, and that he first recorded on the head of his own son. In fact, right now, if you are drifting toward sleep as you listen to this, your brain waves are changing their rhythm, growing slower and wider, sliding toward the patterns of sleep. With the right device, we could watch on a screen how your inner electric storm is calming, how the quick waves of wakefulness give way to the slow, deep waves of rest. You are, from beginning to end, an electric creature. You were born with the spark lit, and with it you will live every instant, until the end. Galvani, with his poor frog legs hanging from a balcony, had glimpsed this immense truth. Life, at its most intimate level, is electricity tamed by biology. We are, each of us, a storm that learned to think. And if it seems astonishing to you that there is electricity inside you, wait until you see what nature is able to do with it out there, in the wild world. From the lightning that opened our story to fish that make hundreds of volts inside their own bodies, nature has been playing with electricity far, far longer than we have, and with a mastery that still leaves us open-mouthed. Let us go back to lightning, to that force that killed Richmond at the start of our story, because now that we understand electricity, we can truly understand what a lightning bolt is, and it is even more impressive than it seems. A bolt of lightning is simply the largest electric spark in nature, the same spark as the electric kiss or the shock from the door handle, but on a colossal scale. It all begins inside storm clouds, those enormous dark clouds that rise kilometers into the sky. Inside them there are violent currents of air that drag ice crystals and soft hail up and down, and they crash into one another without stopping. And in those collisions, just like when you rub a balloon, electric charges are transferred. The particles become charged, the light ones rise and the heavy ones fall, and so the cloud separates into two, with a zone charged one way at the top and another charged the opposite way at the bottom, like a giant Leyden jar charging itself slowly. The difference in charge between the different parts of the cloud and between the cloud and the ground grows and grows until it reaches figures that are hard to imagine. It can exceed 100 million volts. At some moment that tension is so brutal that the air, which is normally an insulator, which normally does not let electricity pass, can no longer hold it, and it breaks. The air ionizes, turns suddenly into a conducting path, and all the accumulated charge discharges at once in a blinding flash. First, an almost invisible ionized channel comes down from the cloud, advancing in jumps, feeling for a path, branching. And when that channel touches the ground, or nearly, the main discharge occurs, the one we see, which actually rises from the ground toward the cloud, along the path already opened. At a speed of tens of thousands of kilometers per second, a fraction of the speed of light, through that channel runs an enormous current, on the order of 30,000 amperes, far more than anything in your house. And that monstrous current, passing through the air, heats it suddenly and brutally. To what temperature? To around 30,000 degrees. Let that sink in for a moment. The air inside a bolt of lightning heats up to about 5 times hotter than the surface of the sun. For a fraction of a second, in that thin channel crossing the sky above your city, there is matter hotter than the surface of a star. That instant heating makes the air expand all at once with explosive violence, and that abrupt expansion is what creates the wave of sound you hear afterward. The thunder. The flash and the thunder are the same event, the light and the sound of the same discharge. You see the lightning instantly because light travels lightning fast, and you hear the thunder a few seconds later because sound is much slower. That is why, by counting the seconds between the flash and the thunder, you can work out how far away it struck. And there is an honest confession that science finds hard to make, but that we make gladly. We still do not fully understand how a bolt of lightning begins inside the cloud. The electric fields we measure in storms seem, curiously, too weak to strike the first spark according to our theories. Something still escapes us in the final detail of the birth of a lightning bolt. It is suspected that perhaps cosmic rays are involved, particles from outer space that cross the cloud and help open the first path, but it is not resolved. After centuries of study, after Franklin and his kite, the force that opened our story still keeps secrets. And there is something beautiful in that the oldest and most impressive electrical phenomenon still holds, in the 21st century, a mystery at its heart. And there are forms of lightning even stranger, which for a long time were taken for the tales of drunkards or the superstitious, until science confirmed them. There is ball lightning, that floating sphere of fire that killed Richmond at the start of our story. A luminous ball the size of a grapefruit that appears sometimes during storms, floats for a few seconds, passes through windows, crosses rooms, and vanishes with a bang or in silence. For centuries, scientists denied it existed because it fit no theory and there were only scattered reports, until too many serious accounts piled up, and some were even captured by chance with instruments. Even today there is no accepted explanation of what exactly ball lightning is. And up high, above the storm clouds, at the border with space, some ghostly luminous phenomena were discovered only a few decades ago, and scientists, with some humor, gave them the names of magical creatures, red sprites, elves, blue jets. They are giant flashes of red or blue light that shoot upward, toward space, from the tops of storms, in the very instant a bolt falls downward. They have existed forever, crowning the storms of the planet, but because they can only be seen from very high up and last 1,000th of a second, they were not confirmed until pilots and astronauts began to glimpse them, and modern cameras could catch them. The storm, that old acquaintance, turned out to have a secret life reaching upward toward the sky that we knew nothing about. The lightning you see fall has an invisible brother that leaps toward the stars. From the electricity of the sky, let us pass to the electricity of the waters, because there are creatures that have turned electricity into a weapon and into a sense. The most famous is the misnamed electric eel, which is not really an eel at all, but a fish of the rivers of South America. This animal is able to generate, in its own body, brutal electric discharges. For a long time it was thought to reach around 600 volts, but a few years ago scientists discovered a new species that reaches 860 volts, the greatest electric discharge produced by any known living being, almost 4 times the voltage of a European plug, generated by a fish in the water. And how does it do it? Here is the marvel and the nod to our story. The body of the electric eel is full of thousands of special cells, the electrocytes, stacked one after another like the disks of a pile. Each cell generates a minuscule voltage difference, a fraction of a volt, but being stacked in series, in a row, their voltages add up, exactly the way the disks of zinc and copper added up in Volta's pile. Thousands of cells, each with its pinch of voltage added together, give the 800 volts of the discharge. The electric eel is, literally, a living voltaic pile. And in fact, the new species that reaches that record was given the scientific name Electrophorus voltae, in honor of the inventor of the pile. Nature had invented the stacked battery millions of years before Volta, and it swam through the rivers of the Amazon while humans still rubbed amber. These fish use their electricity in several astonishing ways. With gentle discharges, they explore the murky water around them, creating an electric field of their own and detecting how objects and living beings deform it. A kind of electric vision that lets them orient themselves and hunt in waters where nothing can be seen. And with strong discharges, they stun or kill their prey, or defend themselves from predators. It has been observed that to hunt large fish, the eel can even coil around its prey to bring the two poles of its body close together, concentrating the discharge, like someone folding a pile over on itself to intensify the blow. And there is something even more incredible. It has been documented that, faced with a large threat out of the water, some electric eels leap out of the river and press their heads against the body of the intruder to discharge directly onto it, a behavior that, astonishingly, had already been described more than 2 centuries ago by the explorer Alexander von Humboldt, who told how the eels of the Amazon leapt at the horses the indigenous people drove into the water to exhaust them before fishing. For a long time, that account was taken for a traveler's exaggeration, until, a few years ago, the eels were filmed doing exactly that, leaping out of the water to discharge onto an obstacle. Humboldt was right, 2 centuries later. Other animals use electricity not to attack, but to see, to perceive the world in a way that is close to us. Sharks and rays have, in their snouts, incredible organs, little gel-filled pores called the ampullae of Lorenzini, detectors of electric fields of an astonishing sensitivity, so sensitive that a shark can perceive the very faint electric field generated by the beating of the heart or the contraction of the muscles of a fish hidden under the sand. Remember that every animal, when it moves its muscles, generates small electrical signals, as we just saw in your own body. Well, the shark can smell that electricity, so to speak, detect its prey by the electric trail of its life, even if it is hidden, even if it is dark, even if it cannot see it or smell it. It can pick up fields of an almost inconceivable faintness, on the order of billionths of a volt per centimeter, a sensitivity that for decades surpassed any instrument we could build. The shark hunts, guided by the electricity of the life of its victims, and those same pores serve them, it is believed, to orient themselves in their great oceanic migrations, sensing the magnetic field of the earth, so that the shark navigates the seas reading, at once, the electricity of its prey and the magnetism of the planet, 2 faces of that same force that Ørsted and Faraday joined together. And to close this walk through the electricity of nature, something tiny and delicate that was discovered very recently, and that is of a surprising beauty. Bees and flowers communicate by means of electricity. It turns out that flowers, anchored to the ground, tend to have a slight negative electric charge, and bees, as they fly and rub against the air, accumulate a slight positive charge. When a bee approaches a flower, that difference in charges is perceptible, and 2 lovely things happen. First, the attraction between the positive charge of the bee and the negative one of the flower helps the pollen leap toward the bee and stick to it, aiding pollination. And second, and this is the astonishing part, when a bee lands on a flower, it alters, for a few minutes, the electric charge of that flower, and bees can detect that alteration with the very fine hairs of their bodies, which move in the presence of electric fields, just as the hairs on your arm stand up near something highly charged. Yes, a bee arriving at a flower can tell, by its electric signature, whether another bee has been there recently and already carried off the nectar, and decide not to waste its time and fly to another. Flowers, without knowing it, leave an electric note that says, "I have just been visited," and the bees read it. A secret electric language between flowers and insects under the sun of the garden that we discovered only a few years ago, and that had been working for millions of years before our blind eyes. And if you look closely, there is a thread that ties together all these wonders of electric nature, from the lightning to the bee. They are all variations on the same theme, charges that separate and then seek to reunite, exactly as in the amber of Thales or the pile of Volta. In the storm cloud, the collisions of ice separate the charges until they leap in a bolt. In the body of the eel, the stacked cells separate the charges until they release 800 volts. In the snout of the shark, the delicate sensors detect the charges that the life of other beings lets escape. Between the bee and the flower, the difference in charges weaves a silent message. And in your nerves, right now, the pumps of your cells separate charges to fire them off afterward in the lightning bolts of thought. It is always the same physics, the same dance of positive and negative, of separation and reunion, repeated at scales and in forms astonishingly different throughout all of nature. Electricity is not a human invention shut inside cables. It is one of the fundamental grammars of the universe, a language the cosmos speaks in the storm, in the fish, in the flower, and in your own brain, one that we, very late, are only beginning to read. Electricity, as you can see, was not invented by us. It was there from the beginning, in the lightning, in the fish, in the shark, in the bee, in the beating of your own heart. We only learned, very late and very slowly, to understand it and to use it. And that use, that taming of the lightning, has built the world you live in. A world that, precisely because it depends so much on electricity, is more fragile than you imagine. Let us come back now to a question we left hanging, and one you may have asked yourself more than once without finding a clear answer. When you turn on a light in your house, where does that electricity come from? Where is it made? How does it reach your plug? The answer is one of the most beautiful things in all of this story, because it brings us back to Faraday and his discovery of 1831, the one I said was the secret key to your modern life. Remember? Faraday discovered that a magnet in motion generates electricity, that if you move a magnet near a coil of wire, current appears. Well, almost all the electricity you use in your life, the one that lights this screen, is born exactly there, from spinning magnets. Think of a power station, any station, a coal station, a gas one, a nuclear one, a hydroelectric one that burns rubbish. However different they may seem, almost all of them do, at bottom, exactly the same thing. All of them are, at their heart, a giant Faraday dynamo. All of them are devoted to spinning enormous magnets inside enormous coils of wire to generate current. The only thing that changes from one station to another is where they get the force to spin those magnets. A coal or gas station burns the fuel to boil water, and the steam under pressure pushes the blades of a turbine and makes it spin, and that turbine spins the magnet. A nuclear station does exactly the same, boils water to move a turbine, only the heat does not come from burning coal, but from the fission of atoms. But the rest is identical: steam, turbine, and magnet spinning. A hydroelectric station uses the force of the water falling from a dam to spin the turbine directly. A wind farm uses the wind to spin the blades of the mills which spin the magnet. In every case, absolutely every case, what happens in the end is the same. A magnet is spun inside a coil, and from there, by Faraday's discovery, electricity flows. Stop to think about the simplicity and the beauty of this. All the fabulous complexity of your electric civilization, all the lights of all the cities in the world, all the computers, all the factories, everything comes down, in its origin, to spinning magnets. Humanity has invented 1,000 different ways to spin a magnet, burning things, splitting atoms, harnessing rivers and winds and tides. But the final gesture is always the same. The gesture Faraday made for the first time with a small copper disc between the poles of a horseshoe magnet. When you turn on the light in your room, you are connected, by a thread of copper that may be hundreds of kilometers long, to a colossal magnet spinning somewhere, pushed by steam or by water or by wind. And that spin is what pushes the electrons that light your lamp. You turn on the light, and kilometers away, a magnet spins for you. It is an image worth keeping for how beautiful it is and for how true. But generating the electricity is only half the problem. The other half is bringing it from those distant stations to the plugs of millions of houses, without losing it along the way. And here is where that advantage of alternating current comes into play, the one that decided the war between Edison and Tesla. The problem of transport is that when electricity travels down a cable over a great distance, it loses energy in the form of heat because of the resistance of the cable itself. The more current passes, the more the cable heats, and the more energy is lost. And here is the brilliant trick. It turns out the losses depend above all on the current, the flow of electrons, and not so much on the voltage, the pressure. So if you transport the same energy, but raising the voltage enormously and lowering the current enormously, the losses shrink dramatically. It is like carrying water at high pressure through a thin pipe, instead of at low pressure through a wide one. And alternating current has the magical property that its voltage can be raised and lowered easily, using a simple device with no moving parts called a transformer, which is nothing more than two coils of wire wound near each other, taking advantage once again of Faraday's induction. So the system works in the following way, and it is a marvel of engineering that holds up your entire life without your noticing. The station generates the electricity at a moderate voltage, before sending it down the great transport lines, those tall towers that cross the countryside with their hanging cables. A transformer raises the voltage to very high figures, hundreds of thousands of volts. At that very high voltage and that very low current, the electricity travels hundreds of kilometers down the cables, losing very little energy. When it reaches near the cities, other transformers lower the voltage in stages. In the substations you may have seen, those enclosures full of equipment and cables. And finally, in one last transformer near your house, the voltage is lowered to the safe level that comes out of your plugs, 230 volts in Europe, or 120 in America. All that dance of raising and lowering the voltage, which makes it possible to bring the energy from so far away, only works well with alternating current. That is why Tesla won. That is why every time you plug something in, you are at the far end of a prodigious chain that begins with a magnet spinning in a distant station, rises to hundreds of thousands of volts to cross the country, and comes down gently to your wall. And there is a detail that tends to be overlooked, and that is astonishing. That whole immense network, the one of an entire country or a continent, works in a synchronized way, all the generators spinning to the same beat, in perfect harmony, like the musicians of a gigantic orchestra, all playing exactly the same rhythm. In Europe, all the generators, from Portugal to Poland, spin in step, marking the same 50 oscillations per second, coordinated to an astonishing degree of precision. If one gets ahead or falls behind, even a little, the whole system notices and corrects it, because a mismatch could spread and bring down the network. It is, literally, one of the largest machines ever built by humanity, a machine the size of a continent, with millions of parts spinning in unison, that most people do not even perceive as a machine. All that immense and silent infrastructure, the electric grid, is a continental organism of cables and magnets and transformers that beats day and night so that you can turn on a lamp without a thought. And it beats with a constant pulse, those 50 oscillations per second in Europe, that invisible trembling running through all the plugs of the continent at once, like a heart shared by hundreds of millions of people. And precisely because of its size and its complexity, it is surprisingly fragile, because that whole network has to be perfectly balanced at every moment, generating, in each instant, exactly the electricity that is consumed, no more and no less, in a continuous and delicate choreography. And when something fails at one point, the failure can spread like a domino tile that knocks down the next, and cause a cascade blackout that leaves whole regions dark in a matter of minutes. That hidden fragility beneath the apparent solidity of our electric civilization is worth pausing on, because it is at once unsettling and revealing of how much we depend on this invisible flow. On the 14th of August, 2003, In the mid-afternoon, in the northeast of the United States and part of Canada, the lights began to go out, not in one house, not in one neighborhood, not in one city, but in whole regions. In a little over an hour, some 50 million people were left without electricity, in one of the largest blackouts in history. New York in darkness, the subway stopped with people trapped in the tunnels, the traffic lights out, the airports paralyzed, the elevators stuck between floors, millions of people walking home under a suffocating heat, with no trains and no air conditioning. And the most astonishing thing is how it all began. It was not an attack, and it was not a great catastrophe. It began with something almost ridiculously small. In Ohio, some high-voltage lines loaded with current on a hot day heated up and expanded, the way any metal expands with heat, and as they expanded they sagged downward and brushed the branches of some trees that had not been trimmed in time. That contact caused a short circuit and disconnected the lines. Up to there, a local, manageable problem. But then it joined with another failure, an error in the computer program that watched over the network, which left the operators without the alarms that should have warned them of the problem. Blind, not knowing what was happening, they could not react in time. And here is where the fragility of the network showed itself in all its crudeness. When those first lines fell, the electricity they carried had to divert through other lines, which became overloaded and began to fall as well, one after another. Each line that fell threw more load onto the ones that remained, which fell in turn, in an unstoppable chain reaction. An electric domino effect that spread at a startling speed across the whole region. In a matter of minutes, what had begun with some untrimmed branches in Ohio had become the collapse of an enormous portion of the northeast grid of the continent, and for the 50 million people who lived through it, it was an unforgettable lesson in how much we depend on something we never see. People trapped in elevators, in the dark, between floors. The subway trains stopped in the blackness of the tunnels, with passengers having to walk along the tracks by the only light of their phones. The traffic lights out, turning every intersection into chaos. The airports paralyzed, the hospitals running with difficulty on their emergency generators, the fridges beginning to defrost, the phones losing coverage as the batteries of the antennas ran down. And something curious and beautiful too, because that night, without the light pollution of the cities, many inhabitants of New York saw for the first time in their lives the starry sky above their heads, the Milky Way spread out over Manhattan. And there were people who called the observatories, frightened, asking about that strange bright cloud crossing the sky, not knowing that it was simply our galaxy, always there, hidden every night by the glow of the electric lights. It took the electricity of an entire civilization going out for people to see the stars again. 50 million people in the dark because of a tree and a software error. That is the paradox of our electric civilization. It is one of the largest and most sophisticated machines ever built, and at the same time it is so interdependent, so finely tuned, that a small failure in the wrong place can bring it down like a house of cards. The more we depend on the grid, the more it hurts us when it fails, and the more we realize, all at once, that almost everything we do rests on that flow of electrons we took for granted. And there is a greater threat, rarer but far more fearsome, that comes from an unexpected place, from the sun itself. The sun, besides light and heat, hurls into space from time to time enormous eruptions of charged particles, solar storms. Most of them do not affect us or only produce the beautiful auroras when they collide with the Earth's magnetic field. But every so often the sun launches a colossal storm, and the greatest one on record happened in September of 1859 and is known as the Carrington event, after the astronomer who observed the solar eruption that caused it. In that era, the only electrical technology that existed was the telegraph, those cables that crossed countries carrying coded messages. And when the solar storm struck the Earth, astonishing and terrifying things happened. The auroras, which normally are only seen near the poles, were seen all over the world, even in the Caribbean and in places near the equator, so bright that people woke up thinking it was dawn. And in the telegraph offices, the machines went wild, the needles moved on their own. Sparks leapt from the equipment. Some operators received shocks, and in several places the paper of the telegraphs began to burn. Some telegraphers discovered that they could disconnect the batteries and go on transmitting messages using only the electricity that the solar storm itself induced in the cables. The sun storm had electrified the telegraph network of the entire planet. Now imagine an event like that, the size of the one in 1859, striking the Earth today. In 1859, the only electrical infrastructure was some telegraph cables. Today, the whole planet is wrapped in a spiderweb of electrical grids, cables, transformers, satellites, electronics, everywhere. A solar storm like Carrington's falling on our current electric civilization could induce enormous currents in the high-voltage lines, burn out the great transformers of the grid, which are huge, extremely expensive, and take months or years to build and replace, and leave whole regions of the planet without electricity for a long time. Serious studies estimate that the damages could run into the trillions and the recovery into years. It is not science fiction. It is a real risk that governments and electric companies study with concern. In fact, in 1989, a much more modest solar storm left the entire province of Quebec, in Canada, millions of people, without power in less than 2 minutes. It happened in the small hours, in the depths of the Canadian winter, with temperatures well below zero. The currents induced by the solar storm overloaded the province's grid, and in barely 90 seconds the whole system collapsed, leaving 6 million people without electricity or heating on one of the coldest nights of the year, for hours. It was a warning of what a greater storm could do. And that night of 1859, the great Carrington event, the accounts that have reached us are almost poetic in their strangeness. Gold prospectors in the Rocky Mountains got up in the small hours and began to make breakfast, convinced it was dawn, fooled by the glow of the auroras. In places where an aurora had never been seen, people came out into the streets to gaze at the sky-stained blood red and green, some marveling, others terrified, believing it was the end of the world, or the reflection of a great distant fire. And while humanity contemplated that celestial spectacle, in the telegraph offices the machines threw off sparks and burned. Our civilization, so powerful, hangs from an electric thread that the sun itself could cut. It is an idea that makes you dizzy, and that at the same time has something of cosmic humility about it. All our technology, all our mastery of the lightning, still stands at the mercy of the largest electric machine in the solar system, the star that gives us life. The same electricity we learned to tame down here, orderly and gentle in our cables, exists up there on a scale beyond imagining, in a sun that is a ball of electric plasma the size of more than 1 million Earths, hurling into space storms able to humiliate our whole planetary grid in an instant. Before we close, it is worth leaning for a moment over the frontier, over what the science of electricity is exploring right now, because the story is not finished. We have spoken of conductors that let the current pass, and of insulators that do not. But there is a third, magical and decisive category: semiconductors, materials like silicon, that sometimes conduct and sometimes do not, and whose conduction can be controlled with exquisite precision. And why is it so important to be able to control whether a material conducts or not at each instant? Because in that, exactly in that, consists all of electronics. A switch that opens and closes millions or thousands of millions of times per second, with no moving parts, governed by other electrical signals. That is what we call a transistor. And it is the brick out of which everything digital is built. Every chip in your phone contains thousands of millions of microscopic silicon transistors, each one letting the current pass or cutting it off. And out of that dance of on and off, of ones and zeros, everything emerges. The numbers, the words, the photos, the videos, the voices, this very story you are listening to. On that ability to control the passage of electrons through silicon, all of modern electronics is built. Every chip, every computer, every phone. Electricity stopped being only force, light, and movement, and became information too. Calculation, intelligence. The same force that Thales saw in the amber, refined beyond imagining, is the one that now thinks inside the machines. And there is another frontier, even more astonishing, that of superconductors. Certain materials that, when cooled to very low temperatures, lose their electrical resistance completely, so that the current flows through them with no loss at all, forever, without spending energy. Remember that resistance was the opposition to the passage of electrons, the one that generated heat and made energy be lost in the cables. Well, in a superconductor, that opposition disappears, becomes exactly zero, and things happen that seem like magic. A current set going in a superconducting ring could spin for years, for centuries, without stopping, with no battery, without losing an ounce of energy. Like a merry-go-round that spins eternally without anyone pushing it. These materials are already used today in some of the most impressive machines that exist, in the magnetic resonance imaging devices of hospitals, in the great particle accelerators, in trains that levitate without touching the rails. Their only problem is that most of them work only at temperatures of extreme cold, near absolute zero, which makes them expensive and hard to handle. And that is why one of the great dreams of current science is to find a superconductor that works at room temperature, with no need of cold. If we managed it one day, it would change the whole world. We would have cables that carry electricity without losing a single drop of energy across whole continents. Infinitely more efficient computers, and many more things we cannot even imagine today. It is one of the great dreams of science right now. The history of electricity, which began with a yellow stone rubbed by a Greek, is still being written today, in laboratories with materials that Thales of Miletus could not even have dreamed of. We have traveled a very long road tonight, and perhaps you are already floating in that soft state between waking and sleep, which is exactly where I want to leave you. Before you go all the way, let me gather up the thread of everything we have seen, slowly, the way you clear the table, without hurrying after a good dinner. We began with a man struck down in Saint Petersburg, Richmond, the first martyr of a force that humanity had only begun to touch. And from there we went back to a yellow stone, amber, that the Greeks rubbed 25 centuries ago, giving, without knowing it, its name to all of electricity. We saw how, for centuries, electricity was only a mystery, a curious spark, until we learned to store it in bottles and make 200 monks leap all at once. We met Franklin, who dared to say that the lightning of the sky and the spark of the drawing room were the same thing, and who gave the lightning an iron bar to tame it. We saw Galvani and his dancing frog legs, and his lovely intuition that life was electric, and Volta proving him wrong in the details while he stacked up the first battery in history. We witnessed the macabre spectacle of Aldini and his shuddering corpses, which inspired the myth of Frankenstein. And we came to Faraday, the poor and humble boy who became the greatest experimental genius of his century, and who discovered the secret that holds up your entire world, that a magnet in motion generates electricity. To Maxwell, the quiet Scotsman, who discovered, trembling, that light, electricity, and magnetism are the same thing, and who gave us radio and Wi-Fi without knowing it. And to Edison and Tesla, the two imperfect geniuses who went to war over which current would light the planet, and who, between the two of them, with their brilliance and their meanness, electrified the world. We also understood what electricity is on the inside, that it is a matter of electrons, those tiny particles of negative charge that flit about in atoms and that in metals can flow, that a current is that flow of electrons, even though each electron moves slower than a snail, while the push travels almost at the speed of light. Like the marbles in the full pipe, we learned what voltage is, the pressure and resistance, the opposition and how they relate. We saw where the electricity in your house really comes from spinning colossal magnets in distant stations, and how it travels at hundreds of thousands of volts to arrive, gentle, at your plug. And we discovered that that immense network, so powerful, is also surprisingly fragile, able to fall because of an untrimmed tree or a storm from the sun. And above all, I hope you take this with you into sleep. We discovered that electricity is not only a matter of cables and machines, that it was in nature long before us, in the lightning hotter than the sun, in the fish that makes 800 volts by stacking cells like a living voltaic pile, in the shark that smells the electricity of its prey, in the bees that read the electric notes of the flowers, and that it is, above all, inside you, right now, that you are, in the most literal and most beautiful sense, an electric creature. That in this instant, while the voice fades and your eyelids grow heavy, your heart beats thanks to a spark it generates all by itself, 60 or 70 times a minute, without rest, since before you were born. That your thoughts, including the faint, diffuse thought that accompanies you now toward sleep, are orderly electric storms crossing the geography of your brain. That every sensation of your body, the weight of the blankets, the softness of the pillow, travels to your mind like a tiny bolt of lightning down the highway of your nerves. Galvani, with his poor frogs hanging from the balcony, had glimpsed this immense truth more than 2 centuries ago. Life is electricity that learned to organize itself, to feel, to think. You are a silent, warm storm that lasts as long as a life lasts, and right now that storm is calming. Your brain waves are turning slow and deep, the quick waves of the day giving way to the slow waves of rest, in that electric transition that happens every night inside your head, and that is perhaps one of the most mysterious and most ordinary phenomena in the universe. You are falling asleep, and that too is electricity, a soft change in the rhythms of the storm, so let yourself go. You do not have to remember anything we have told. There was never any exam. I only wanted to keep you company for a while through the most astonishing story there is, the one of how humanity tamed the lightning, and the one of how the lightning, in truth, lived inside us from the very beginning. While you fall asleep somewhere kilometers away, a colossal magnet goes on spinning in the darkness of a station to keep the world lit. And inside your chest, much closer, another small spark goes on beating. Faithful, tireless, watching over you while you rest. The two of them, the one outside and the one within, the one that lights the cities and the one that makes your heart beat, are the same ancient force that Thales found in a yellow stone, the same one that killed Richmond on a stormy evening, the same one that now, gentle and silent, carries you softly toward sleep. Rest well. Sleep deep. And dream, if you like, of distant and gentle lightning, of magnets spinning in the night, of the serene and perfect storm that is you.